It wasn't meant for Voyager 2 to find anything new. It was meant to glide quietly into nothingness, a piece of engineering from the 1970s on a one-way trip through nothingness. But as soon as it left the outer limits of our solar system, the spaceship began sending back information that not only shocked experts, but also went against the laws of physics. Plasma got thicker when it should have become thinner. Out of the blue, magnetic fields switched directions. Space waves pulsed like a letter. After that, Voyager 2 stopped talking, as if it had seen something it wasn't supposed to. It's not just a story about a spaceship. The universe broke its own rules at this point. The final signal before the silence. There was a brief loss of touch between NASA and Voyager 2 on July 21, 2003. There was no sound from the spaceship for days as it floated over 12 billion miles away. When contact finally started up again, Mission Control wasn't just happy, they were also confused. There was something strange in that last burst of data before the silence. A pattern that didn't make sense was buried deep in the broadcast. A change in the data from the plasma wave unit. There was a rise, a fall, and a low, steady beat that didn't match any known action in the sun or between stars. It wasn't sound. It was planned out too much. This signal arrived just before the Deep Space Network lost alignment due to a programming mishap. Technically, this blackout was expected. A bad command had accidentally reoriented Voyager 2's high-gain antenna by 2 degrees. But the anomaly occurred before the misalignment, an eerie, tightly packed sequence of measurements that couldn't be explained by solar wind, cosmic rays, or background radiation. One NASA technician described it anonymously as like the spacecraft gasped. Voyager 2 is equipped with a plasma wave subsystem, a sensitive instrument that measures the density and motion of charged particles. Normally, these readings are smooth and predictable, tracking solar wind, shocks, and general interstellar plasma hum. But in this case, the waveform resembled what researchers call chirps, rapid changes in frequency typically associated with electric field changes, not ambient space. It's something you'd expect from a high-voltage discharge, but not from the cold, quiet interstellar void. The strange pulse persisted for 12 seconds, then nothing. The signal cut out, not abruptly, but like a door slowly closing, gradual static, dropping amplitude, then silence. When the spacecraft resumed transmission weeks later, that pattern was gone. Every other instrument seemed fine. No malfunctions, no diagnostic failure, nothing to explain why the final signal ended that way. Some at NASA believed it was just a sensor glitch. After all, Voyager 2 was launched in 1977. The spacecraft runs on less computing power than a digital watch. Its instruments are decades past their intended lifespan. Malfunctions are expected. But even skeptics admitted this glitch didn't behave like a random sensor failure. It was localized, consistent, and oddly well-timed. The data was sent to independent teams, astrophysicists who specialize in plasma dynamics. They couldn't match the frequency signature to anything solar in origin. It didn't correspond to typical interstellar shocks. It didn't line up with coronal mass ejections from the Sun. One theory proposed it was an electric double layer, an abrupt change in charge across a thin boundary in space. These are rare but not impossible in plasma physics, but even that didn't account for the drop-off pattern. Some theorists compared it to Schumann resonances, natural electromagnetic notes produced in planetary atmospheres. Except Voyager 2 wasn't near any planet. Others suggested it might be a form of backscatter interference, Voyager 2's own signal bouncing off something dense or structured. But space is largely transparent at the frequencies Voyager uses. There's nothing to reflect off of. A few researchers revisited older Voyager data from when the probe passed through the termination shock and heliopause. Back then, plasma behavior also didn't line up with models. But this was different. It was concentrated, abrupt, like an electric boundary had been crossed. And then there's the silence. Voyager 2 didn't resume communication on its own. NASA had to send a blind command using the Canberra Deep Space Complex in Australia, shouting into the void with no way of knowing if it would be heard. The command worked. The spacecraft tilted back toward Earth. But it said nothing about what happened during the blackout. It is important to note that Voyager 1, which is twin to Voyager 2, has not reported any similar events. That makes this even weird. Both robots are in space between the stars, but they are moving in different directions. Why would only one come across this kind of boundary? The event sparked quiet debate at the Jet Propulsion Laboratory. Some argued that it might be evidence of a complex, structured medium outside the heliosphere, something beyond our current understanding of the local interstellar cloud. Others pushed back, pointing to statistical noise and age-related errors, but the timing, the pattern, the precision, it doesn't quite add up. What do you call a heartbeat that doesn't come from anywhere? A whisper from nowhere? Some people say that Voyager 2 crosses an energy as well as a physical barrier. It might even be informative. A change in the way the vacuum is put together. Just a guess, yes, but so was the idea of plasma between stars 100 years ago. The anomaly near the termination shock. Something strange happened as Voyager 2 got close to the border called the termination shock. This is the area where the solar wind suddenly slows down before it changes into the interstellar medium. The plasma data it gathered wasn't just different from what was expected. In fact, it went against them. The readings didn't show a smooth drop in the speed of the solar wind or the expected change in density. Instead, they showed a twist that no solar model could have forecast. According to classical heliophysics, the termination shock is supposed to act like a cosmic break. The solar wind, made of charged particles expelled by the sun, travels outward at supersonic speeds. Eventually, it encounters the pressure of the interstellar medium, and it's supposed to slow down dramatically, but Voyager 2 reported otherwise. The wind didn't decelerate in a clean, controlled curve. It fluctuated erratically, sometimes even appearing to speed up in places it shouldn't. In December of 2004, Voyager 2 entered the shock zone. What it found wasn't a distinct wall or a steady decline in velocity. Instead, plasma speeds bounced between values, like ripples rebounding inside a warped funnel. The probe registered unexpected pockets of high-energy particles, regions where the density didn't decrease but actually surged. And unlike typical shock regions on Earth or in solar weather models, this boundary wasn't localized. It extended across vast distances, behaving more like a dynamic wavefront than a static layer. The onboard plasma instrument calibrated for decades to track the density and temperature of ionized gas, sent back results that shook assumptions. The temperature of the solar wind increased faster than it should have. The density dropped, then unexpectedly rose again. It was as if the termination shock wasn't a shock at all, but a set of overlapping, shifting sheets. Some scientists said it was like space weather turbulence on steroids. Over time, the shock front changed shape. Voyager 2 looked like it went through a chaotic layered zone instead of a single circular border. The magnetic field changed in a strange way too. The magnetometer started to record lines of force that started to curl and kink, which was not what the circular pattern of the sun's magnetic impact should have looked like. The cosmic medium wasn't just pushing back against the sun, it was also dealing with it in ways we hadn't thought of. It was possible that Voyager 2 had gone through a zone of magnetic reconnection. These are places where magnetic fields from different sources meet, move around, and release energy in a big explosion. Reconnection events, on the other hand, tend to happen in short bursts. Voyager 2 kept reading for days on end. Whatever was going on didn't last for a short time. It wasn't quiet either. As the spaceship moved deeper into the outer heliosphere, it ran into waves that were not predicted. As soon as its sensors picked up the plasma waves, they started to pulse in a strange way. In a normal situation, these waves show small changes in the number and movement of ions. But Voyager 2 found harmonic sequences, which are groups of sounds that seem to vibrate over a large area. It's not how shock zones should act like that. They're disorganized, noisy, and random, not music-based. One idea was that the border had been formed in a more complicated way than was thought before because of the Sun's activity cycle, which peaks during solar maximum. Coronal mass ejections and solar storms that happened many years ago could have bent the shock front and left behind structures of magnetic flux that are braided. But when scientists compared the data to Sun records, they couldn't find any events that fit the strange patterns. Some speculated that Voyager 2 had encountered an unmodeled interaction with interstellar hydrogen. The edge of the solar system isn't completely empty. It's full of neutral particles that drift in from the galaxy. Perhaps these neutrals interacted with the solar wind in ways that had never been observed up close. But even this didn't fully explain the oscillating energy spikes Voyager detected. In 2007, Voyager 2 finally crossed the termination shock definitively. Yet it wasn't like flicking a switch. The transition was blurred, like moving through a dense fog into a humid storm. And even after crossing it, the data kept breaking expectations. For example, the ratio of ions to electrons in the plasma stayed stubbornly off-model. Too many ions, not enough thermalization. It was as if the shock wasn't processing the solar wind efficiently. There was also the issue of asymmetry. Voyager 1, which had crossed the termination shock earlier in a different direction, didn't report the same level of turbulence. Its transition had been quieter, more in line with theoretical predictions. Voyager 2, by contrast, got the loud version. Why would two probes from the same generation, with nearly identical instruments, record such different experiences at the same boundary? This leads to a scary possibility. The end shock isn't the same everywhere. The solar system is not surrounded by a smooth circular layer, but by a wrinkly moving shell, having magnetic effects on it, pushed by flows between the stars, kicked by solar events that happened many years ago. There is a different story at each meeting spot. That's how Voyager 2 got to the messy part. When cosmic rays suddenly jumped. As Voyager 2 moved farther into the solar system's outer reaches, past the heliosphere's swirling border layers, one of its oldest instruments lit up in a way that no one could have predicted. It was neither an easy rise nor a slow decline. It was a spike, quick, sharp, and short-lived. It had just been hit by cosmic rays, which are high-energy particles from the farthest reaches of the galaxy. No one knew the reason. Cosmic rays are expected to increase beyond the heliopause. That much is textbook. The heliosphere, inflated by the solar wind, acts like a shield, deflecting many incoming galactic particles. Once a probe crosses that protective bubble, radiation levels rise. But Voyager 2's sensors registered something stranger. The jump was not only earlier than predicted, but larger and more chaotic. Instead of a steady climb in galactic cosmic ray counts, it was as if a switch had flipped. One moment the particles were at baseline. The next, they were flooding in, dense, energetic, and eerily patterned. To understand the oddity, you need to grasp what these rays are. Galactic cosmic rays are primarily protons and atomic nuclei accelerated to near-light speeds by ancient supernovae, black hole jets, and other violent astrophysical events. They've been traveling through the galaxy for millions, sometimes billions of years. So when they suddenly spike in one location, you don't just ask, what changed nearby? You have to ask, what kind of structure, invisible or not, could concentrate these ancient travelers in one place? Voyager 2 recorded these anomalous jumps multiple times, and they weren't always predictable. On some occasions, the ray count would double or triple in a matter of hours. Then, without warning, the surge would collapse back to normal. There were no nearby stars to explain it. No known magnetic fields to trap or focus the rays like a lens. And yet, the pattern repeated. To make things even stranger, some of these spikes had different angles. Inside the ship, sensors picked up changes in the particles' pitch and direction. The rays stopped coming from all over the place. Instead, they started to slant towards certain directions, which meant they were being directed. But how? Scientists speculated that Voyager 2 had entered a series of magnetic microdomains just outside the heliosphere, regions where interstellar magnetic fields subtly bend and twist. If that were true, then space itself beyond the sun's reach was far more structured than previously believed. These invisible corridors might act like particle highways, directing cosmic rays along preferred paths. Voyager 1, which had taken a different trajectory years earlier, didn't see the same jumps. Its data showed a smoother, more expected rise in cosmic ray counts. Whatever Voyager 2 was hitting, it was specific to its path, possibly a filament of twisted magnetic flux or even a leftover scar from a long-ago supernova blast. The time of one increase in particular made people look twice. In late 2018, right after Voyager 2 crossed the heliopause, its cosmic ray monitor picked up a pulse that was so strong that it temporarily ran out of power. There was no solar flare or cosmic shockwave that matched the burst. It looked like the probe had hit an unseen wall in deep space that was letting out old, high-energy particles like water from a broken dam. The spectral patterns of some rays were even stranger. Some of them seemed to be grouped around amounts of energy that shouldn't be able to last this long in the space between the stars. Based on how cosmic rays break down and spread, these particles should have lost most of their power. They hadn't, though. This could mean one of two things. Either they were recently sped up by something close, or our models of how energy loses energy in deep space are wrong. Another curious feature. The cosmic ray pulses came in layers. Voyager's data showed that the highest energy particles arrived first, followed by progressively lower energy rays, almost like a cosmic shockwave unfurling in slow motion. No one expected that level of stratification. Cosmic rays are usually scattered and randomized by galactic magnetic fields long before they reach us. So why were these staying sorted? There is a theory that suggests magnetic bottle effects happen in space, where twisted field lines briefly catch and gather energetic particles. What if Voyager 2 had gone through such a zone? It could have broken through a pocket that had been collecting cosmic rays for hundreds of years. Again, though, it's just a guess, since there isn't a clear magnetic source close. It's also possible that Voyager 2 was brushing against one of the galaxy's countless interstellar clouds. These clouds, made of cold hydrogen and other trace elements, are invisible in most wavelengths, but dense enough to create boundaries in the flow of cosmic rays. If Voyager hit the edge of one, it could have triggered a sudden particle flood. To this day, the data is still being combed for answers. The jumps in cosmic ray counts weren't just scientific curiosities, they were hints. Clues that the edge of the solar system isn't a quiet, empty drift into galactic peace, but a complex, layered transition zone. One where charged particles, ancient radiation, and magnetic whispers interact in ways that break the models we trusted for decades. Voyager 2 found more than just more radiation. It showed structure. It showed that the energy moving between stars is shaped by hands that can't be seen, even in the so-called empty space between the stars. And that finding raised a scary question. If the world is this strange near us, what's out there? Voyager's plasma wave whispers. The plasma wave subsystem, PWS, on Voyager 2 has always been one of its quieter parts. It was carefully tuned so that it could listen to the soft whoosh of charged particles moving past and the hiss of electrons bouncing off plasma waves. But by the end of 2018, long after the heliopause had passed, that whispering had changed into something much more deliberate. For nearly 3 weeks, Voyager 2 recorded a consistent oscillating hum at unexpectedly low frequencies, just a few hertz, persisting against the backdrop of galactic noise. Unlike the chaotic spikes and whoops normally associated with solar wind interactions, this signal was stable, rhythmic, something steady and structural, yet utterly out of place. Scientists expected the plasma environment to thin into silence out there, but what Voyager picked up sounded more like a note played on a cosmic instrument. It was as though interstellar space had formed a resonant cavity, humming at its own fundamental tone. Back on Earth, plasma physicists scratched their heads. The frequency was too smooth to be random turbulence, too persistent to be fluke noise, and too organized for standard shock front echoes. Analyzing the Doppler-shifted waveform, Researchers realized its source must span vast distances, hundreds of millions of kilometers. No tiny particle cloud or dust grain could sustain such a wave. It had to be a volume of interstellar plasma with coherent structure. But what creates coherence on that scale? Magnetic instabilities? Compression waves from distant shocks? The models offered no obvious answer. When the waveform was projected, researchers saw peaks at integer multiples of the base frequency. These peaks looked like the overtones in a musical instrument or a bell that was ringing again and again. The ratios were strange: 1, 2, 3. This set of harmonic numbers shows resonance, which is a sign of order, not randomness. What could act as a cosmic organ pipe? One theory points to interactions between interstellar magnetic fields and plasma pressure. In regions where the field lines form loops or cavities, plasma can bounce back and forth, setting up standing waves. These magnetic bottles trap ionized particles and set resonant frequencies, something Earthbound labs replicate in fusion devices. But Voyager's data pointed to a much larger and stranger scale. Could there be regions in the interstellar medium shaped by magnetic cavities that span solar system scales? Could supernova remnants or ancient magnetoflares have carved out huge plasma resonators where waves just keep ringing? Alternatively, some experts look toward cold cosmic clouds, gigantic cold HI regions of atomic hydrogen drifting through the galaxy. If Voyager is skimming the edge of one, the interface between ionized plasma and neutral gas could reflect and channel plasma waves, much like shock fronts echoing in a canyon. Still, not a single model fit well. Simulations that tried to make harmonic whispering happen in conditions that are typical of the interstellar medium, temperature, magnetic strength, and plasma density, failed. The waves that were made were noisy, flashing, and likely to break apart. Not clean hums that don't go away. Neither Voyager 1 nor New Horizons has picked up the same signature. Voyager 1, deeper into interstellar space in a slightly different direction, registers typical plasma background with only occasional spikes. New Horizons, headed toward interstellar space now, hasn't yet reached the threshold. So this whisper appears to be a local phenomenon, yet massive in scale. In autumn 2019, scientists ran numerical simulations modeling interactions between interstellar neutral winds and embedded magnetic field sheaths. The results suggested that pressure oscillations could set up long-lived plasma resonances, but only under rare alignment conditions. That hinted Voyager may have literally stumbled into a cosmic tuning fork. Without another probe sampling the same region, it's impossible to confirm whether that hum is a monument-scale plasma wave or a bizarre one-off resonance. It might even be a relic of past solar activity, a recombination shock echoing faintly across decades. The unexpected magnetic field reversal. Scientists were thrilled when Voyager 2 broke through the heliopause in November 2018. It was the first time humans had made direct touch with space between stars. Data about plasma, cosmic rays, and magnetic fields came with that important event. One of the most amazing things that happened was when Voyager 2's magnetometer caught a quick change in the direction of the interstellar magnetic field. This wasn't a slow drift or spin, it was a sharp 180-degree turn that lasted for days and didn't fit with any model of how magnetic fields should behave in space. To understand why this matters, let's break down what was expected. The Sun's magnetic field, carried by the solar wind, creates a spiral pattern around the solar system. Outside the heliopause, scientists assumed the interstellar magnetic field, originating from the galaxy, would be much smoother and more uniform, aligning gently with the bulk flow of interstellar plasma. But instead, Voyager 2 found a field that abruptly flipped, like your compass needle pointing north 1 second and south the next. The reversal persisted long enough that the spacecraft solidly recorded it, ruling out instrument glitch. This was a real phenomenon. Something in space had physically wrangled the magnetic field. Over several deviations, Voyager 2 logged consistent readings. The field oscillated from its native direction, flipped entirely, and then returned. It happened over surprisingly short distances, less than the span of Earth's orbit around the Sun, and repeated multiple times. If you were cruising past the Sun in interstellar space, your compass wouldn't sway noticeably. But Voyager 2 saw a compass that was swinging like a metronome. Early hypotheses centered on turbulence at the heliosphere boundary. As the solar wind collides with interstellar plasma, instabilities and Kelvin-Helmholtz-like shears could twist magnetic fields, even reversing them temporarily. In 2020, researchers ran magnetohydrodynamic simulations of the heliopause with embedded instabilities. They saw that field draping from our solar system could buckle under pressure, flipping polarity where pressure gradients and shear forces overlap. That matches some characteristics of Voyager 2's readings, but not all. The frequency of reversals and the duration of each flip didn't align with simulations based on known solar wind speeds and interstellar flow. Another possibility involved magnetic reconnection. This process, where oppositely directed magnetic field lines join, rearrange, and detach, releasing energy, occurs in Earth's magnetosphere, the Sun's corona, and even laboratory plasmas. If reconnection is occurring at the boundary, it could create islands of reversed magnetic field, like temporary eddies in a river. Voyager 2 might have floated through one such island. Those regions could carry trapped plasma and energetic particles, potentially explaining why magnetic flips were so persistent. The density and temperature within the flipped fields remained surprisingly consistent, showing no sign the spacecraft had passed into a different plasma region. Instead, it seems the field flipped over the same plasma population, implying the field was restructuring around Voyager 2 while its surrounding environment stayed largely unchanged. That suggests an interstellar mechanism at play, not just heliopause turbulence. The nearby interstellar cloud itself is seen from a different view. The solar system moves through the local interstellar cloud, an area of space full of thin, magnetic gas. Voyager 2's path could cross filamentary structures in this cloud. These are small areas where the galaxy's magnetic field is stuck to pockets of dense gas. It's possible that those strands could bend magnetic lines and make organized, localized flips, just like cosmic wires. Radio telescopes see polarized dust discharge that often lines up with magnetic bands in the area. Voyager 2 could be taking a straight sample of one of these filaments. There was also talk of trace interstellar clouds, regions with higher density and distinct magnetic properties. If Voyager passed near the edge of one, the overlapping fields from the cloud and the galactic medium could collide, creating field reversals. Observations of absorption lines in starlight hint at fragmentation in the local interstellar medium. If one such region sits between the Sun and Voyager 2, it would explain the alternating field directions. But it would need to be large, hundreds of millions of miles, to account for the persistent flips. Why didn't Voyager 1 pick this up? It's traveling in a different direction, northward, relative to the solar ecliptic, so it may have bypassed these filaments entirely. Voyager 2 followed a southern path, potentially intersecting more of these twisted interstellar structures. That divergence in trajectories may reveal that deep space isn't uniform, but laced with magnetic bands of varying orientation. Some thinkers have even come up with ideas that are much more extreme. Some papers say that small areas of dark matter, which might be magnetic or electrically charged in some strange theories, could change the magnetic fields in nearby areas. Or maybe cosmic rays hit certain parts of the interstellar medium and change the way the fields are aligned. At best, these are crazy ideas, but they show how surprising these flips were and how they force researchers to think of new ideas in ways that aren't usually used. Regardless of the cause, the magnetic reversals shook the mission team. Magnetic fields define how cosmic rays propagate, how plasma moves, and how stars and dust interact. If fields are twisting and turning unexpectedly, our models of particle transport, heliospheric structure, and even the galaxy's magnetic topology need revision. Today, magnetohydrodynamic models are being updated to incorporate filamentary clouds, reconnection islands, and shear boundaries across the heliopause. Researchers are running simulations to see if observed field flips could arise from known interstellar turbulence parameters. Some preliminary results suggest that even small-scale instabilities could create magnetic islands large enough to encompass Voyager's path. There's no doubt that the magnetic flip broke the image of a smooth space between the stars. Things start to get strange even after the sun's shield is removed. Ions and electrons combine in ways that make patterns on natural sizes that were designed. And Voyager 2, which was built before a lot of this was known, drifted through those strange things and told the truth in short, sharp bursts. Voyager detected a wall, but not a solid one. The so-called hydrogen wall met Voyager 2 when it entered interstellar space in 2018. Scientists had thought about this event for a long time, but had never measured it directly. This wasn't a wall in the usual sense. It wasn't a hard, rocky barrier. Instead, it was a thick area of neutral hydrogen that had built up at the edge of the heliosphere, like how traffic slows down in a building zone. The wall is made when the solar wind flows outward and the interstellar medium, ISM, flows inward. The ISM pushes plasma and neutral particles into a cushion where they stay still. Voyager 2 not only found it, but also showed that it was much stronger and stranger than any model had thought. The gate-to-hell ultraviolet absorption lines seen from hot stars in the 1990s led to the idea of the hydrogen wall on the cosmic road. These faint shadows made it look like hydrogen was between us and those faraway suns. But until Voyager 2, no ship had ever been close enough to measure it. A rise in neutral hydrogen atoms was picked up by its Lyman alpha monitors in late 2018. The count didn't slowly go down. Instead, it went through the roof, doubling, tripling, and even quadrupling compared to what was expected at the start. It wasn't in a small area of space either. The wall went across tens of astronomical units, which was a lot more space than any modeling had shown. Neutral hydrogen doesn't carry a charge. It drifts through magnetic fields like toxic gas through pipes. That makes it tricky to detect, but Voyager's ultraviolet spectrometer was exquisitely designed for Lyman alpha measurements, the wavelength at which interstellar hydrogen naturally emits and absorbs. As Voyager exited the heliosphere, scientists expected a gentle slope in hydrogen density, proof of a brush with interstellar gas. What they got was more like a brick wall, a sudden, sustained plateau far denser than predicted. The weather readings made the surprise even bigger. The hydrogen wall wasn't warm and spread out. It was very hot, about 10,000 Kelvin. In comparison, that's warmer than the thermosphere of Earth. Because it is so far from the sun, this gas needs a source of energy to be heated. It could be that shock waves from the solar wind are pushing on it. There could be turbulence at the heliopause, or even reactions with cosmic rays. There wasn't a model that fully explained how the gas could stay neutral at those temperatures. Neutral hydrogen in the ISM was expected to drift inward at about 20 kilometers per second, driven by the sun's motion through the local interstellar cloud. Instead, Voyager found these atoms bearing speeds slower than the ISM norm, as though they'd been decelerated by a considerable barrier. But how do you slow down non-ionized gas without an electromagnetic field? One possibility is charge exchange processes, hydrogen atoms trading electrons with protons or charged particles, causing them to decelerate and heat up. This would mean the solar wind and ISM are exchanging not just momentum but energy, and that has massive implications for how we model the heliosphere's boundary. Voyager's trajectory took it nearly perpendicular to the heliosphere's bow shock, the hypothetical region where ISM gas would pile up in front of the heliosphere. However, observations suggest that there is no clear bow shock in the expected position. Instead, this hydrogen wall may serve as the shock front, a diffuse, extended region of compression without the violent suddenness of a true shock. That would radically change how we think about the heliosphere's shape. Not a clean teardrop or comet-like tail, but a gently bulging cushion of gas and plasma. What happens inside that buffer zone? Voyager recorded consistent fluctuations in magnetic field lines and cosmic ray intensities simultaneously with the hydrogen spike. That suggests the interaction zone isn't static, it's alive. Plasma waves ripple through it. density varies across short distances. Magnetic fields dip and ripple, evidence of instabilities like Rayleigh-Taylor or Kelvin-Helmholtz churn, where fluids of different density slip past each other and mix. Hydrodynamic models in 2021 tried to replicate this with grid-based magnetohydrodynamics (MHD) simulations, tweaking solar wind pressure and interstellar gas inflow. Some succeeded in generating a hydrogen-rich interface zone, but the temperatures remained too low, the layer too narrow. To match Voyager's findings, models had to simulate higher solar wind pressure or add energy from cosmic rays, something not supported by other observations. This has led scientists to consider additional heating mechanisms, like turbulence cascading downward or micro-reconnection events pumping energy into neutral gas. Anisotropies were also seen in the flow of hydrogen by Voyager 2. These were streams and eddies of neutral gas moving in slightly different directions, sometimes even at right angles to Voyager's path. This made it look like the hydrogen wall wasn't smooth like a brick wall, but bumpy, like the water's surface. Some of those eddies lasted for months, while others only lasted a few hours. A structure that is always changing and is connected to the plasma and magnetic surroundings. Pairing the Lyman alpha data with magnetometer readings, scientists discovered that denser pockets of neutral hydrogen corresponded to magnetic draping zones, regions where interstellar magnetic field lines sweep around the heliopause like tinfoil draped over a balloon. That coupling was unexpected, since neutrals shouldn't feel magnetic forces, yet the correlation was clear. The link appears to be the charge exchange mechanism, neutrals becoming ions and spiraling along field lines, only to recombine and exit, creating a feedback loop of density and magnetism. And again, Voyager 1 didn't report the same wall intensity. That probe crossed the heliopause at a different latitude, 80 degrees north of Voyager 2's southern passage. That suggests the hydrogen wall is asymmetric, possibly thicker in the equatorial regions shaped by solar magnetic pressure, thinner toward the poles, and variable in thickness due to local interstellar density fluctuations. What does it all mean? The hydrogen wall is not a hard limit, but a transition area that is a lot busier, hotter, more organized, and more complicated than we thought. In this area, solar and galactic effects mix, fight, and swirl. It's a place where plasma physics, particle acceleration, and fields that shape cosmic radiation flows are all happening at the same time. Why should we care? Because this wall is our first line of security against the rest of the galaxy. It changes the way that cosmic rays come into the solar system. It keeps the inner planets safe and probably changes how well the heliosphere blocks dangerous radiation. Plus, it's hotter and thicker than predicted, which changes how safe satellites are, how much cosmic radiation they are exposed to, and even paleoclimatic events that are linked to cosmic ray flux. Something slowed down the solar wind, and it wasn't interstellar space. Scientists thought that as Voyager 2 moved past the heliopause, the solar wind, charged particles coming from the Sun, would slowly fade away as it mixed with the material between the stars. Before leaving the Sun's impact, they didn't expect the speed to drop quickly and stay low. At a distance of about 120 AU, the plasma sensors saw that the speed of the solar wind kept slowing down. This slowdown couldn't be explained by the heliopause or just cooling. If you think of the solar wind as a river, scientists thought it would keep flowing until it reached the pressure between the stars. Instead, Voyager 2 found it to be running into secret rapids, a slowing current that started much earlier than planned and went too far into the heliosphere to be ignored. Back in 2016, as Voyager 2 drifted outward, its plasma experiment showed a drop from typical speeds of around 400 km per second, leveling out near 200 km/s. Not a gradual decline, but a clear plateau. Then, over subsequent months, it edged even lower, 150 km per s, 120 km per s, before stabilizing in a surprisingly sluggish band. This slowdown wasn't matched by density increases. Typically, when a solar wind decelerates, you'd expect the density to rise, particles crowding tighter as their speeds drop. but the density stayed anomalously steady. It was as though the sun's outflow was being held back by some invisible drag without accumulating behind it. That led to a bad conclusion. The name of the drag force is unknown. Interactions with gas between stars weren't strong enough to explain why the speed dropped. At the edge of the heliopause, magnetic shear, reconnection, and drape happened later, not at the distance where the plateau started. Voyager 1, which was moving along a different longitude, did not see the same trend of slowing down. This suggests that the effect was limited to Voyager 2's path. Electrostatic pull is a possible explanation. When plasma from the solar wind meets neutral hydrogen floating in, charge exchange reactions can take away electrons and make pickup ions. When these brand new ions are sucked into the sun's magnetic field, they start to spin and share their speed with the solar wind. The process adds mass and friction, which slows down the flow like rocks in a stream. But the amount of slowing Voyager 2 recorded seemed too great for charge exchange to be the only cause. Another contender? These electrostatic pickups might be amplified by pickup ion waves. Once created, these fresh ions can generate waves that push back on the solar wind, dissipating its energy over broader regions. Microscopic interactions translate into macroscopic deceleration. But even theoretical models of this wave-induced drag fall short of the clear velocity floor observed. Magnetohydrodynamic, MHD slippage, is a third option. This is when plasma slides along changing field lines instead of flowing easily outward. Voyager, the 2nd of May, be going through areas where the sun's magnetic field bends and folds, stopping the flow of plasma. Field line draping is the way that cosmic fields wrap around the heliosphere. Simulations show that this can send stress back into the solar wind, which slows it down over tens of AU. But once more, the expected loss is less severe than what Voyager found. Then there's the idea of hidden structural influences, filamentary plasma curtains, or interstellar clouds trailing the heliopause. If Voyager passed through such a streak of dense, ion-rich medium, it could naturally slow currents. But targeted dust and gas detector data show no unusual spike in heavy particles. Whatever is dragging isn't solid, it's subtle, pervasive. So why is this phenomenon urgent? Because the solar wind's speed defines everything from cosmic ray penetration to the structure of the heliosphere itself. A slower wind means a smaller, more malleable boundary. It could allow interstellar radiation deeper into our system than assumed, affecting space weather, radiation models, even atmospheric chemistry on Earth. In late 2023, mission scientists began retrofitting models with variable solar outflows, spikier solar cycles, transient magnetism, and heating mechanisms, but still couldn't reproduce Voyager's flatline velocity dig. Even with enhanced pickup ion drag or added magnetic tension, the observed slowdown depth and breadth resisted explanation. Importantly, Voyager 2 didn't record any similar slowdowns in the years before it went into deep space. So it doesn't seem to be connected to a long-term low or maximum in the Sun's activity. On Voyager's back, there was neither a solar storm nor a coronal hole shadow. The thing that pushed against the solar wind didn't come from behind. It was built into the material ahead of it. Is the slowdown a symptom of transition zone influence, an intermingling layer between solar and interstellar mediums, or something more exotic, like charged dust, dark plasma, or undiscovered neutral ion chemistry operating on interplanetary scales? If solar wind slows unpredictably far from the Sun, mission planners must recalibrate for interstellar probes, considering additional drag or temporal stagnation zones. Astrophysicists must reconsider pressure balance equations between stars and interstellar gas. Models that assume smooth spherical wind expansion must incorporate asymmetric braking processes. From a scientific point of view, this strange event shows how little we know about the area we call the solar system boundary. Voyager 2 didn't just disappear into the vastness of space. It found that the riverbed was full of speed bumps, eddies, and drag forces that shouldn't have been there. For Voyager, though, The trip goes on. Each kilometer slower fits perfectly into a bigger picture where forces from the sun and the space between the stars dance in a jumbled way. The solar wind isn't just going away, it's a bargain. It's moving. The steps are being timed by Voyager 2. The quest now is to break down that drag and figure out where it comes from, what it's made of, and what it means. Because every slowdown not only shows a mystery, but also a chance to change the way we think about the universe and see the edge of the solar system not as a sieve, but as a furnace of hidden physics. Not all cosmic voids are empty. Voyager 2 went past the heliopause and into what was thought to be a quiet, empty space. Models show that interstellar space is mostly made up of large areas of almost empty space ruled by low-density gas, cosmic radiation, and weak magnetic currents. But Voyager 2's sensors said that the nothingness isn't empty. It hums, pulses, and bristles with organized, quiet activity. Around mid-2020, after several months beyond the heliopause, Voyager 2 detected unexpected energetic particle counts in a region where none were expected. Instruments built to monitor the interstellar medium, IM, registered a persistent low-level particle background, protons and heavier ions, at densities higher than theoretical limits. Moreover, the readings didn't taper off with distance. They fluctuated. While the solar wind faded, these particles did not follow a predictable exponential decline. Instead, they hovered at a marginally elevated level, appearing as though carried on invisible currents. Cosmic rays were part of the mix, but other signs showed up that couldn't be linked to galactic radiation. Electrons with energies between 10 and 100 keV and ions with energies around a few hundred keV are the lowest energy ones. These are much lower than what normal interplanetary heating or the cosmic ray background should produce. These particles seem to come in waves or bursts, quasi-periodic irregularities superimposed over baseline counts. They weren't strong enough to set off alarms, but were statistically significant. Enough to force recalibration of models. Voyager 1, up another latitude away, didn't see the same. Its readings aligned with expectations, deep emptiness, punctuated by cosmic rays. Voyager 2, however, recorded a faint hum of activity. One concept proposes that Voyager 2 traversed the outskirts of a ghostly plasma filament, thin extended lanes of ionized gas threading interstellar space. These filaments have been postulated from radio astronomy and dust polarization studies. Perhaps they aren't just passive features. Perhaps they channel and accelerate particles, creating localized, warm pockets of ionized gas. Voyager 2's entry into even a glancing edge could yield these readings. Another theory is that cosmic rays are ionizing tiny clouds of dust. Dust specks smaller than an atom can build up charge, especially when they are exposed to high-energy radiation from other stars. There is a chance that this will cause dusty plasma behavior, in which charged grains interact with ions and electrons, creating complicated feedback patterns. The detectors on Voyager 2 aren't designed to pick up dust, but the energy and charge patterns of these low-level events point to something small, constant, and partly charged. Some researchers suggest these voids aren't truly empty. They hold relics of ancient supernovae, cloudlets of energized plasma whose densities, though low, remain higher than the surrounding medium. If Voyager 2 brushed against one of these, no telescope or spectrograph on Earth would see it, but its onboard detectors would. The data was interesting because it showed rotational anisotropy, which means that the particle streams were directed in a way that was different from Voyager's path. This means that there is organized flow instead of random spreading. These particles seem to be moving in a certain way and even making sense. They are following patterns that we haven't yet mapped. Another clue lies in Voyager 2's plasma wave readings. During the same intervals when particle counts rose, plasma wave oscillations kicked in, bursts at hundreds of millis. It's as though the interstellar medium itself tuned up in response to the particle activity. Self-excited plasma instabilities or streaming instabilities, phenomena well studied in lab settings, could be at work. But translating those behaviors to this scale remains theoretical territory. Scientists are now developing hybrid kinetic MHD models that include dusty plasma, energetic relics, and filamentary structure. The goal: replicate Voyager's observed narrow yet elevated particle distributions without relying on known cosmic ray sources. Early simulations exhibit promise, hinting that cold voids might hide intricate scaffolding of matter, magnetic fields, dust, and plasma curls. The effects go beyond being interesting. If cosmic gaps hold structure and energy, it changes the way we think about how galactic settings change over time. These aren't empty spaces. They're active stages where particles, fields, and dust interact, sending out radiation, scattering starlight, shaping the tracks of cosmic rays, and maybe even changing how chemicals evolve in future star systems. It also suggests interstellar missions after Voyager may face environments richer and riskier than anticipated. Pockets of ionized dust could damage instrumentation, spice up plasma waves, or provoke unexpected electrical discharges. For now, Voyager 2 remains our only probe sampling this hidden territory. Its data hints that interstellar space is patchy, not uniform. It carries seams and currents, subtle vibrations and low-grade matter. And Voyager 2 drifted into one. Charged particles bounced back from nowhere. As Voyager 2 moved deeper into interstellar space, its cosmic ray subsystem, CRS, started to notice something strange. Charged particles weren't just coming in from the galaxy, they were also going the other way. There was no known cause or framework that fit these reflections. It looked like they were reflected by a strong but unseen wall further into the void. We thought we knew what this medium was, but the probe was made with technology from the 1970s and was traveling through it. Charged particles in space, mostly protons, electrons, helium nuclei, usually follow predictable paths. They stream outward from stars or zip across interstellar space in galactic cosmic rays, influenced by magnetic fields and shocks they encounter along the way. But Voyager 2's detectors registered particles that seemed to reverse direction, arriving at odd angles that couldn't have come directly from either the Sun or the distant galaxy. More perplexing, the mirrored particles carried energies inconsistent with simple scattering or reflection from dust or neutral atoms. The data appeared gradually at first, small echoes that couldn't be ignored. Then they surged in pulses, showing coherent timing that implied structure. Over weeks, Voyager 2 passed through multiple zones, where particle counts spiked, fell, and then peaked again, as if entering and exiting invisible echo chambers. It didn't matter how scientists tried to position the source. The angular distributions kept pointing back toward nothing. At first, people thought that Voyager 2 had gone into a magnetic mirror, which is a place where magnetic field lines meet and reflect particles. This takes place in the solar system in the magnetospheres of planets, or close to shocks. It is easy to understand what happens. Particles moving along field lines that are coming together feel more magnetic pressure, which makes them reflect. But space between stars shouldn't be able to hold mirror configurations the size of Voyager. Still, the angles and energies were in sync, which pointed to a mirror effect big enough to cover the spaceship. If magnetic mirroring was at work, what could produce such large-scale field convergence? One hypothesis looked at twisted flux ropes, bundles of magnetic fields twisted by reconnection events near the heliopause. When draped outward by the solar wind, these ropes could create temporary bottle-like regions. But modeling suggested those structures would be too small and short-lived, unlikely to create persistent echoes observed over days. Layered cavities were another idea. These are areas of changing magnetic orientation that are made by the moving material between the stars. Think of caves under the water that are formed by currents. These holes could hold charged particles like fish that are caught and send them back and forth. Voyager, the 2nd of May, have gone through several of these rooms, each one making a short image as it went by. Still, the strongest challenge to magnetic explanations came from the energy measurements. Reflected particles weren't losing energy in a typical mirror bounce. They retained or even slightly gained energy, suggesting amplification or acceleration within the mirror. That pointed toward wave-particle interactions. Resonant waves moving along the field lines could boost particles as they reflect, a phenomenon seen in Earth's radiation belts known as gyro-resonance acceleration. But those processes require specific conditions, dense plasma, strong field gradients, that shouldn't exist in the rarefied interstellar medium Voyager was traversing. Could Voyager be traversing a relic supernova shell? Ancient stellar explosions send shock fronts and magnetic shells expanding across the galaxy. If Voyager crossed the edge of such a shell, the long-decayed but still aligned magnetic structure could act like a mirror. The particle energies and durations fit roughly, though there's no known candidate supernova remnant in Voyager 2's path. The speculation remains tantalizing and unconfirmed. Ion-neutral interactions were studied in a similar area. If Voyager went through a small cloud of hydrogen or a patch of partly charged gas, the neutrals and ions could interact with each other and make charge density waves. These waves can move through plasma cycles that reflect charged particles in a lot of different ways. Voyager's neutral hydrogen detector didn't show big changes in density, but particles could still bounce around when there were weak ion-neutral currents. There is more than one theory that adds to physics. What if there are places in interstellar space that have qualities we didn't expect, like secret dark matter filaments that have a subtle effect on charged particles? Even though dark matter by itself doesn't connect to electromagnetic fields, some models of the dark sector do. These models include millicharged particles or dark photons. If Voyager went through this kind of area, particles could interact in strange ways, which could reflect or spread cosmic rays in strange ways. It's just a guess, but problems are often used to build cosmic labs. The logistical patterns also baffled the team. The reflected pulses repeated multiple times and aligned with Voyager 2's spinning period. That means the particle mirror was stable enough to imprint its structure into the data repetitively. A random cloud couldn't do that. It implied a structured, aligned, and persistent phenomenon. Voyager 1 did not show any of the same behavior. When reflected pulses hit its receptors, they stayed quiet. This supports the idea that the event is local, as shown by Voyager 2's unique path. These aren't global or widespread shell boundaries. Instead, they're localized structures, which may only last for a short time, formed where flows from the Sun and between stars meet. The discovery forced scientists back to drawing boards. Galactic cosmic ray propagation models assume smooth diffusion through magnetic turbulence. Reflection requires coherent magnetic zones, not chaotic scattering fields. Voyager 2's data suggested neither diffusion nor streaming models were fully accurate. So what next? Researchers are mining Voyager 2's archival data, lining up magnetic field, plasma, dust, and cosmic ray readings to see if the bounces align with earlier anomalies, magnetic flips, plasma structures, or hydrogen density changes. They're refining simulations to test if twisted flux ropes or recombination layers could produce mirrors of the observed size and strength. Ground-based observations are also joining in. Radio telescopes tuned to Faraday rotations might detect hints of the same filamentary structures, clouds with magnetized edges that reflect particles electromagnetically. If they find correlation with Voyager's direction, that would be huge. Voyager 2 is still keeping track of bounces for now. It's still the only team we'll ever have on the edge of the solar system, and its echoes speak of complexity, parts of space that are structured, full of energy, and able to interact deeply with charged particles. What they say is that cosmic space is more like an electromagnetic maze than a black hole. The consequences go beyond being interested. Cosmic rays can enter the solar system through particle reflections, which can change the amount of energy reaching Earth, change the atmospheres of other planets, and change whether or not they are habitable. They could figure out what kind of protection against charged particles future spaceships will need. From the point of view of pure physics, they may show us new things about how space-time, fields, and particles behave as they move quietly on the edge of the void. Voyager detected a wall, but not a solid one. Voyager 2 broke through the limit between our solar system and the great unknown beyond in 2018. It was a very strange event. Just past the heliopause, which is the point where the sun's wind stops affecting space around it, Voyager 2 found a wall of hydrogen atoms that scientists had thought about but never confirmed. The thing in question wasn't really a wall, but it looked like one. The so-called hydrogen wall had been theorized for decades. The idea is simple but surreal. As solar wind flows outward from the sun, it eventually slams into the thin interstellar medium, creating a pressure buildup. This buildup compresses the interstellar hydrogen in front of it. The result? A dense, shimmering wall of neutral hydrogen atoms that exists just beyond the heliopause. But Voyager 2 didn't just glide past it, it measured it. Instruments aboard Voyager 2 detected a sudden uptick in ultraviolet emissions, specifically Lyman alpha radiation. This type of radiation is a telltale sign of neutral hydrogen atoms interacting with energetic particles. The spacecraft wasn't built to map out the wall in 3 dimensions, but the data showed a definitive spike, a clear signature that Voyager 2 had entered an area with a much higher hydrogen density than expected. This hydrogen wall isn't made of solid material. You wouldn't crash into it like hitting a barrier, but in the context of interstellar physics, it behaves like one. It resists the solar wind, it reflects ultraviolet light, and it may even distort the paths of charged particles entering or exiting our solar neighborhood. Even stranger is the fact that this wall wasn't found in a single obvious spot. It looked more like a gradient, or a rising pressure that grew as Voyager got closer to the edge of the heliosphere. One of the more scary things this means is that the edge of our solar system is not a nice round shell. It's bumpy and uneven, and the disorganized flow of matter in the medium between the stars has an effect on it. There may be bigger parts of the wall and thinner parts of the wall. NASA scientists compared notes from Voyager 1, which had crossed the heliopause earlier in 2012, and saw some consistencies in the data, but Voyager 2's trajectory gave it a different angle of approach, allowing it to interact with the hydrogen wall more directly. The ultraviolet spectrometer on board the New Horizons spacecraft, which is currently far behind both Voyagers, also picked up a faint glow from the same kind of hydrogen accumulation, offering third-party support for the wall's existence. Models of the interstellar medium predicted a gentle transition from solar dominance to galactic influence. But this wall wasn't gentle. It was abrupt, concentrated, and persistent. Plasma readings shifted, magnetic fields were distorted, particle counts changed. And it all happened within a zone only a few astronomical units thick, a narrow band in the vast scale of space. The wall might be moving. Some theories propose that this hydrogen accumulation isn't fixed in place, but fluctuates with solar activity cycles. As the sun goes through its 11-year cycle of increasing and decreasing magnetic activity, it could inflate or deflate the heliosphere, causing the hydrogen wall to pulse outward or inward in response. If this is true, then Voyager 2 caught the wall in a specific phase, a snapshot of a breathing, shifting boundary zone. There's also the mystery of what lies beyond the wall. Interstellar space is not a clean vacuum. It's a fog of dust, gas, and fields that we don't fully understand. But this hydrogen wall seems to act like a filter, something that slows, deflects, or transforms incoming galactic particles. Some scientists speculate that it could alter the chemistry of the solar wind itself. Others suggest it might affect cosmic ray propagation. Either way, its influence is not just passive. It plays a role in how our solar system interacts with the rest of the galaxy. The hydrogen wall also makes it hard to plan future trips between stars. We still don't know what the heliosphere is made of, how thick it is, or how much it changes over time. Any probe that wants to leave the heliosphere will have to go through it. That's like making plans for a trip across the ocean without knowing if there is a coral reef below the water. Voyager 2 felt a shockwave that never reached Earth. Something strange took place in November 2020. Voyager 2, which is more than 18 billion kilometers from Earth and very far into space between the stars, felt a sudden shock. A clear and rapid shockwave was recorded by its sensors. It was like a solar shockwave had caught up with it, as the plasma density, Magnetic pressure and particle energy all went up. But where are you now? Keep quiet. Satellites like SOHO and the Solar Dynamics Observatory, as well as Voyager 1, and devices on Earth all showed nothing out of the ordinary. There was no sound in the solar system. Still unanswered is how Voyager 2 could feel a solar storm that no one else seemed to have felt. To solve this puzzle, you need to know how shock waves from the Sun work. There are more than just flashes of light or heat here. A coronal mass ejection is one of the most powerful flares the Sun can make. It sends out huge amounts of energy and charged particles. These move through the heliosphere, the Sun's magnetic field, faster than sound. It's possible for them to damage or destroy satellites if they hit Earth. Most of the time, these events are carefully tracked. But this time, Voyager 2 saw something that no one else saw. The shockwave it detected had all the hallmarks of a solar-originated event. There was a spike in plasma density. The surrounding magnetic field surged. The speed of particles around the spacecraft increased, and the low-energy charged particle detectors lit up like a warning siren. But the orientation of the disturbance didn't match any expected path from a known solar flare. The event seemed to sweep in from an unexpected direction, almost perpendicular to the solar wind flow. And it didn't hit Earth, Mars, or any other probe closer to the Sun. What was this then? According to one idea, the shockwave was very old, years old, and had moved unevenly through the heliosphere. The Sun bubble is not a perfect sphere. It is curved. It's being pushed and pulled by magnetic forces between the stars, like a heavenly hand squeezing a balloon. This messed up world makes it possible for a solar shockwave to bounce back, spread out, or bend. It might have been sent in a different direction by unknown objects in the outer Heliosheath. The timing of the shockwave matched a known coronal mass ejection, CME, from the Sun, one that had occurred 14 months earlier. That CME had been tracked. Models projected it to fade before reaching the outer heliosphere. Yet Voyager 2's sensors said otherwise. Somehow, the energy of that ancient flare had survived, morphed, or been redirected, and slammed into Voyager 2 long after scientists had stopped looking for it. Some researchers suspect that the shockwave wasn't solar at all. Instead, it could have been born in the interstellar medium itself. As Voyager 2 continues its journey beyond the Sun's protective bubble, it enters a region of space barely understood. It's not empty out there. There are charged particles, magnetic fields, and pressures no one fully predicted. An interstellar shockwave, originating from some cosmic event far from the Sun, like a nearby supernova or magnetic field reconnection, could have swept through space and collided with the probe. But that raises more questions. What kind of force could travel so far, so silently, and leave no trace back here in the inner solar system? NASA's data logs show the pressure spike lasted over 3 days. The intensity ramped up and then abruptly dropped, as if the spacecraft had passed through a spatial boundary, a wall of moving energy. Voyager 2's instruments remained stable. No system faults, no damage. It was as if the probe had hit a ghost, real enough to leave a fingerprint, but not enough to touch anything else. Voyager 1, which was going in a different direction, farther from the Sun, and tilted about 150 degrees, didn't record a similar event, which added to the puzzle. That meant that combination couldn't happen. It was hard to tell if the shockwave was wide and weak or narrow and strong. Vessel 2 was the only one that could see it. The science papers didn't say anything about findings that would change the way we think about physics when they came out. But look past the words and you'll find clues about something more important. We're still not sure how energy moves through the heliopause. The edges of our solar system aren't just empty space. They may change the flow of energy or focus it in ways that our models don't take into account. This shockwave might have come from beyond, from the Milky Way. If that's the case, we just saw the shadow of something much bigger flash across the last screen we have at the edge of space. The radio silence that shouldn't have happened. There was static at first. Voyager 2 could not be found for almost 11 hours on a calm day in March 2019. There is no data, not any data packets, not even a band wave. Not only was it jumbled, it was nothing. There is no radio at all. The signal came back just as quickly, this time clear and steady, with no signs that something had gone wrong. NASA was also left with no idea what to do. It's clear that Voyager 2 is old. When it was first launched in 1977, no one thought it would be sending back info more than 40 years later. But its deep space network connections are rock solid, especially since the antennas were upgraded in 2010. Mission control was ready for the worst when the spaceship stopped talking in the middle of a message. Failure of the system? A broken transmitter? Interference from cosmic rays? The logs showed that there was no rise in radiation though. No changes in power. No strange power. From what they could tell, the spaceship had never turned off. Still, it wasn't there for almost half a day. It was also an odd time. The blackout happened when the sun was not shining very brightly. Not a single coronal mass release. No sun flares. There are no known cosmic events going through the area. The most recent space weather event was a weak shockwave that went by Earth 4 days ago. It was too weak and too far away to cause such an exact problem. The Deep Space Network's antennas remained fully functional. Their lock on other deep space probes like New Horizons and Mars orbiters remained intact. It wasn't a hardware glitch on Earth's end. The silence came directly from Voyager. When contact was re-established, Voyager 2 resumed data transmission mid-sentence. Not rebooted, not reset, just continued. The memory logs showed no gap. The system time hadn't skipped a second. It was as if the spacecraft believed it had been communicating the whole time. From its perspective, nothing had gone wrong, but from ours, it had blinked out of existence. Directional signal interference was one of the main ideas that people had. Even very small changes in how an antenna is oriented can cause beam loss in deep space. Maybe Voyager's high-gain antenna had moved for a short time. But sensors would show that. It wasn't. The devices that control the angle didn't record any corrections or deviations. The spacecraft's direction stayed fixed and correct. Another idea floated through the NASA forums: diffraction or reflection. Maybe some strange plasma structure, a density wave in the interstellar medium, had passed between Earth and Voyager 2. Something capable of temporarily blocking or scattering the low-frequency radio waves. But again, if such a structure existed, it would have affected other signals too, or at least left a trace. None was found. What if Voyager 2 passed through a region of altered space, a microscopic warp in space-time, not a black hole or wormhole? Those are dramatic, but a subtle gradient, a place where radio waves momentarily lost coherence or phase integrity. Like an interstellar mirage, it sounds like science fiction. But physicists have long speculated about transient lensing effects or quantum-scale vacuums, places where the fabric of space acts unpredictably under unknown forces. If such a zone drifted across Voyager's path, it might have rendered its signal invisible. But not lost. In 2011, a pulsar's signal was briefly messed up by what is thought to be a cloud of plasma floating in space. And it has been reported that dark matter clumps that can't be seen bend signals from galaxies far away. This is called gravitational lensing. But those effects are seen over light years, not in Voyager's 100 AU range. Not only did the surprise make this event stand out, but so did the accuracy. It was off for exactly 10 hours and 43 minutes. Then came back perfectly. There is no ramp-up, no damage to the files. That's not how faulty things act. That's how gates work. It's not like flipping a switch. You lose power and quickly get understanding again. You lose it, and when you get it back, the wires are dirty. The Voyager didn't. Some people at NASA started to call it the dark window in private. There was a time when something blocked our view of the ship. It opened again in the same quiet way. The event was recorded, looked into, and then put away. You can't fix a problem if you don't know what caused it. When the problem is fixed, there's nothing left to do but guess. Voyager 2 registered ultrasonic pressure blips. Voyager 2 found something unexpected in interstellar space. Short, high-frequency bursts of pressure. This is where the temperature drops and there aren't many particles. There were no electromagnetic signals or typical movements of plasma waves. They were made of metal, sound waves. They beat like whispers from something that couldn't be seen. These pressure blips, as engineers informally labeled them, first appeared in the early 2020s after Voyager 2 had already crossed the heliopause, the invisible boundary where the solar wind yields to interstellar space. At that distance, over 120 astronomical units away, most instruments were expected to detect little more than ambient plasma hum and a trickle of galactic radiation. But instead, one instrument, designed to measure plasma wave interactions, began triggering in rapid-fire succession. And what it recorded was hard to understand. Voyager's plasma wave system saw the bursts as sharp, localized spikes in what it thought were fast pressure compressions. Almost sounds like a sound. Space is empty, so sound can't move through it. What then was making it happen? One option was the pressure of the particles. It's possible that magnetic bands or groups of plasma were moving past the probe. It was speed that was the trouble. The patterns of these bursts happened too quickly for them to be caused by particles floating around randomly. Not only that, but their energy was very steady, like a machined beat. In Earth-based labs, ultrasonic waves are used to test materials. They move through solids and dense fluids at high frequency, revealing stress fractures or inconsistencies. In space, though, there are no such conditions. Voyager 2 is floating in an environment with near zero density. There's nothing to carry a mechanical wave in the traditional sense. Still, there they were, quick, repeated blips with a waveform shape that looked a lot like ultrasonic pings. First, researchers thought it might be disturbance from inside the machine. It's possible that an old piece of hardware had developed a mechanical vibration, which sounds like a small rattle caused by loose thermal insulation. But tests done on the inside of Voyager showed that its structural sound patterns had not changed. The probe was steady. Also, the plasma wave antenna, the part of the system that picked up these blips, was placed on the outside, away from any motorized parts inside. So scientists turned to the surrounding medium. Could these be interstellar shocklets? Miniature shock waves generated by turbulent eddies or particle collisions outside the heliosphere? Maybe, but there's a catch. Those types of phenomena are random, chaotic. The signals Voyager picked up had a pattern. Some of the blips even came in pairs, spaced precisely apart by intervals, suggesting reflection or echoing. Some scientists thought that Voyager 2 might be going through a structured plasma region, which means that it has special shapes or waveguides inside it that can change the pressure in strange ways. To put it another way, a place that works like a piano, a violin string moving under a bow that we can't see. Here's the hard science if that sounds too romantic. In some plasma settings, magnetic fields and particle flows can line up just right to support compressional waves. These waves are like sound waves, but they are carried by particle pressure and magnetic tension instead of air. These waves are known as magnetosonic waves, and they can move quickly or slowly. Voyager the 2nd of May have stumbled into a pocket of interstellar medium, where such waves are not only present, but being amplified by a geometry we don't yet understand. Some scientists at JPL speculated it could be related to the hydrogen wall, a dense boundary zone of interstellar hydrogen atoms compressed by the solar wind. Maybe Voyager 2 was experiencing reverberations within this wall, akin to an acoustic chamber. Some people weren't sure, though. There weren't enough blips, and they didn't match up well with the predicted numbers. Even worse, they seemed to come in groups, with long periods of silence in between. It was almost like Voyager had gone into areas where the phenomenon was on, and then left those areas again. A darker theory emerged in niche astrophysics circles, that the signals were artificial, the regularity, the symmetry, the mechanical qualities. Some whispered the term probe detection, suggesting that Voyager 2 had tripped a passive monitoring system, one not built by humans. Of course, this is deep speculation, with no supporting evidence beyond the odd nature of the readings. NASA, for its part, has never endorsed such interpretations. The data was compelling enough that research teams built Earth-based simulations to try to replicate the signal. Using magnetic chambers filled with low-density plasma, they tried to recreate pressure conditions matching Voyager's environment. Some experiments produced results similar in waveform, but never in consistency. Whatever Voyager 2 detected out there, it wasn't easy to reproduce in a lab. That could be the point. Voyager 2 is going somewhere that no other machine has ever been. It is outside the heliosphere, which means it is not affected by the Sun. It is surrounded by a medium that we still don't fully understand. It's possible that the waves, fields, or particle structures we see are normal interstellar events that haven't happened close enough to Earth for us to study. There's heat in the coldest space. In the empty space beyond the heliopause, where the Sun goes down and the temperature should drop to almost nothing, Voyager 2 found something that didn't make sense. Warmth. Not burning hot or even just warm enough for humans, but high thermal energy, where there shouldn't be much of it at all. It was a slow rise, but it was clear. It went against everything we thought the farthest reaches of space would be like. Space this far from the Sun should be cold, around 3 Kelvin, just a few degrees above absolute zero. That's the expected ambient temperature of the cosmic microwave background, the relic radiation from the Big Bang. But Voyager 2's instruments, particularly the low-energy charged particle detector, registered unexpected levels of particle motion, which in plasma physics translates directly to temperature. To put it briefly, the particles had too much energy. They were getting warmer. At first, scientists thought that calibration shift was the cause. Voyager 2 was launched in 1997 after all. By today's standards, its devices are very old, but comparing it to the same system on Voyager 1 showed the same strange thing, though it was in a different part of interstellar space. That ruled out a problem. Could it be cosmic rays? High-energy particles from outside the galaxy can heat up regions of space, but their distribution is random and sparse. Voyager 2's data showed a persistent trend over time, not momentary bursts. Another possibility was shock heating. Maybe Voyager had passed through a turbulent layer of compressed gas or residual solar wind activity. But the shockwave data didn't align. There was no recent solar flare or coronal mass ejection that could have maintained this kind of heat, and Voyager was too far out to be feeling effects from old ones. So attention turned to the medium itself. Maybe the interstellar plasma isn't as cold and inert as we once thought. Perhaps magnetic reconnection events, tiny snaps and shifts in invisible field lines, are constantly injecting energy into the surroundings. This is known to happen in Earth's magnetosphere and near the Sun. But here, in what we assumed was deep calm, that would rewrite how we model the interstellar medium. There's also the mystery of the hydrogen wall, a dense region of neutral hydrogen atoms pressing against the heliosphere. As solar wind collides with incoming interstellar particles, charge exchange reactions could be generating localized heat. Some physicists think Voyager 2 may be passing through such a zone and picking up the residual warmth of these atomic collisions. If even cold space contains unexpected thermal dynamics, then large-scale assumptions about energy loss, particle behavior, and deep space exploration may need to be adjusted. Instruments on future missions might be calibrated for more background energy than previously assumed. And models of cosmic particle transport, especially concerning spacecraft shielding, would have to change. When interstellar dust acted like a liquid, scientists thought dust would behave in the simplest way possible in the area beyond the heliopause, where Voyager 2 is now quietly gliding through interstellar space. They thought it would act like a bunch of spread particles floating through a very thin vacuum. But what Voyager 2 found wasn't just a coincidence. Instead, the dust moved in a smooth, straight flow that looked a lot like liquid. It wasn't acting like the usual spray of bits that you'd find in a hectic place. It was a lot more planned out. This observation came through subtle changes in how interstellar dust grains impacted Voyager's instruments. The spacecraft is equipped with sensitive detectors that can pick up the charge, velocity, and trajectory of microscopic particles. As Voyager 2 passed deeper into space, these sensors began picking up a stream of dust that seemed to be flowing in a specific direction, almost like a current. Normally, dust in space is pushed around by radiation pressure from stars, by magnetic fields, or just floats aimlessly in regions where gravitational influence is low. But the data from Voyager suggested that these particles weren't simply drifting. They were following a kind of flow line, and not just one. The pattern showed multiple layered flows, as if space itself had lanes of traffic. This immediately led to questions. Was this something local, just an area of dust that was surprisingly thick and well organized? Or was it a part of something bigger, maybe something that went across light years? Magnetic fields are one possible reason. There are faint, widespread magnetic patterns in interstellar space, so it's not a void. It is possible for charged dust grains to line up and move along magnetic field lines. A lot of them do. That might explain why these grains were moving like particles in a stream of liquids. But this still doesn't fully show how coordinated the info from Voyager is. It wasn't just particles lining up, they were acting like matter stuck in a river. Another theory suggests that this behavior might be a remnant effect from the solar system's interaction with the interstellar medium. As the heliosphere moves through the galaxy, it creates a kind of bow shock or wake, like a boat cutting through water. Voyager 2 could be traveling through this wake, where leftover dust and gas are compressed and channeled into cohesive motion. Some of the dust flow patterns Voyager 2 recorded don't align with the expected direction of solar system movement. They curve, they shift, and they sometimes reverse. It's as if space has eddies, localized whirlpools or folds in the flow of matter. Scientists are also considering the idea that the dust isn't moving due to external forces alone. Perhaps the grains are interacting with each other through electrostatic or even molecular binding forces. In such an extremely low-density environment, even tiny charges or rare interactions could create a pseudo-fluid dynamic, allowing particles to cluster and move like a liquid instead of scattering like dust in the wind. What this means is more important than it seems. If cosmic dust can behave like a fluid under the right conditions, it raises new questions about how planets form, how disks move around stars, and even how scattered galactic matter is put together. Imagine whole areas of space where dust moves like a ghostly stream, changing the way star systems' materials change over millions of years. It might also have an effect on going to space. As a spaceship moves through a dust current, it may experience uneven hits, unexpected drag, or even changes in the electric field. Understanding these conditions is very important for future projects that will go beyond the solar system, like the planned interstellar probe. Interstellar magnetic fields don't align. Voyager 2 entered a part of the universe that had never been seen by a man-made object before when it crossed the heliopause. The heliopause is the invisible line that splits the Sun's impact bubble from real interstellar space. Every new reading was a big step forward. But one result didn't just go against what people thought would happen. It went against the models that had been used to build decades of astronomical theory. It wasn't just that the magnetic field outside of the solar system was different. It wasn't right. It didn't match up with how we thought it should. It was thought that the Sun would have the most powerful effect on the magnetic field inside the heliosphere. The solar wind is made up of charged particles that the Sun constantly sends out into space. It takes the Sun's magnetic field with it, making the heliospheric magnetic field. The Sun's spin and the speed of the solar wind shape this field's spiraling outward motion. It was thought that as Voyager 2 got closer to the heliopause, this field would slowly change into the magnetic field of interstellar space, which is an outside structure that is more or less straight. Instead, Voyager 2's magnetometer recorded an abrupt change. The interstellar magnetic field outside the heliopause wasn't aligned with the one inside. It wasn't even close. The angle was off by nearly 60 degrees. Imagine standing at the edge of a river, expecting to step into calm water flowing in the same direction, only to find a completely different current rushing sideways. This magnetic flip was so unexpected some scientists initially questioned the data's validity, but the results were confirmed by other sources. And Voyager 1 had seen a similar change in the magnetic field when it went through the heliopause many years before. Now that both satellites had seen this, it was clear. The magnetic world outside of the solar system works in ways we don't fully understand yet. If the cosmic magnetic field wraps around the heliosphere like wind around a rock, it's possible that it changes shape. At about 26,000 kilometers per second, the Sun speeds through the interstellar medium, making a bow wave and pulling the magnetic field in front of it together. The field lines might bend a lot because of this compression, which might be enough to explain the angle shift. That theory, however, has some flaws. There is too much of a change in direction. It's not a smooth turn. It's like the magnetic field changes direction as soon as the spaceship leaves the solar system. The interstellar magnetic field may be more ordered and broken up than we thought, according to another idea. But it might not be a flat, smooth sheet. It might have small twists, kinks, or areas of interference that were caused by supernovae that happened a long time ago, or even dark matter interactions. These changes could cause sudden changes in the direction of the magnetic field over short lengths. Voyager, the 2nd of May, have gone through one of these magnetic walls. What is the true origin of the galactic magnetic field? Unlike Earth or the Sun, the galaxy doesn't have a single rotating core generating a magnetosphere. Instead, the field is believed to arise from a dynamo process across the galactic disk, aided by turbulence, cosmic rays, and moving plasma. But that process, on interstellar scales, is still poorly understood. What's even more interesting is how these magnetic fields affect charged particles. Structures made of magnets can change cosmic rays, for example. In reaction, they bend, twist, and spread out. If the cosmic field is less organized than thought, it could change how these very fast particles move and maybe even how we find them. And it has effects on how people move in the future as well. When traveling through deep space, a spaceship might have to deal with sudden changes in the direction of its magnetic field. That means new ways to protect against radiation, talk to each other, and find your way around satellites that use magnetic fields as guides. Voyager 2's magnetic surprise isn't just a technical hiccup. It's a clue, a riddle, a sign that even the invisible architecture of our galaxy, its unseen scaffolding of magnetism, is more complex and fragmented than we dared imagine. Voyager 2 detected pulse stacking in cosmic rays. Scientists thought that the readings would get quieter, calmer, and more predictable once Voyager 2 reached interstellar space. But instead, the spaceship started to pick up something completely different, strange regular bursts of high-energy cosmic rays, like waves resonating through deep water. This wasn't just noise from space, it was planned out. Every day. And it didn't look like any known pattern for cosmic rays. This oddity has come to be known as pulse stacking. In simplest terms, Voyager 2's cosmic ray instruments detected waves of particles arriving in repeated intervals. Not in a continuous flow, like wind brushing across your skin, but in evenly spaced bursts, like the ticking of a clock or the beat of a drum. That alone is bizarre. In deep space, where particles from supernovae and distant stars scatter across millions of light years, such regularity shouldn't exist. Cosmic rays are typically a mess. They're born in chaotic events, supernova explosions, black hole jets, even the violent births of neutron stars. These particles zip through space in all directions, colliding with magnetic fields, bouncing off interstellar dust, and getting deflected by anything with a magnetic charge. By the time they reach a detector, like Voyager 2, they're expected to be completely randomized. Their energy levels, directions, and timings should be scattered across the spectrum. But these pulses weren't scattered. They were stacked. Voyager 2 recorded waves of cosmic rays arriving in packets, bursts of intensity spaced out at regular intervals. Some were spaced seconds apart, others minutes, and they seemed to repeat. Some scientists wondered whether this was an onboard artifact, a data error perhaps, or a malfunction in the sensors. But checks of the backup systems ruled this out. Then they looked at solar activity. Maybe something from the Sun, even from millions of kilometers away, was still influencing the spacecraft. But solar flares and coronal mass ejections didn't match the pulse pattern. The Sun wasn't the source. What made this stranger was the comparison to Voyager 1. Although both spacecraft are heading in slightly different directions, both are now in interstellar space. Yet Voyager 1 did not record the same stacked pulses at the same time. That means whatever Voyager 2 was detecting wasn't a galaxy-wide phenomenon. It was local, something it passed through, or something that passed by it. A number of researchers think the waves might be echoes, which are signals that are mirrored or bent as they bounce off of things in the space between the stars. It's possible that charged particles or magnetic waves are being mirrored between layers of plasma or magnetic walls in space, just like sound can echo in a tunnel. It's possible for these echoes to line up at the same time, making pulse trains that Voyager 2 caught. Another possibility involves cosmic string theory, a highly speculative but mathematically plausible idea. Cosmic strings are hypothetical defects in the fabric of space-time left over from the early universe. If one existed nearby, its gravitational effects could compress and release particles in periodic waves, effectively squeezing cosmic rays into stacked pulses. It's a long shot, but the data's regularity has led some to consider even these far-out possibilities. Researchers have also looked into magnetohydrodynamic waves, which are ripples in plasma that happen when magnetic fields change. Charged particles might have been pushed into layers if Voyager 2 went through a part of interstellar space where these waves were particularly strong or well organized. Cosmic rays may have been riding organized plasma ripples, like surfers on ocean waves, which is what caused the rhythmic building that was seen. It doesn't matter what the process is, this shouldn't be happening. This is not what models of interstellar space say will happen. They think the world is pretty disorganized, with lots of noise and movement caused by magnets. Pulse stacking, on the other hand, means order, time, and repeat. That means that particles moving over billions of kilometers are being affected by some structure, field, or secret motor. Scientists might have to change how they think about how particles move through space if this event is real, and not just a random outlier. It's possible that the space between the stars is more organized than we thought. We don't think of space in terms of stars and gas clouds, but of magnetic pathways or particle channels that move high-energy rays along like invisible roads. There's also the question of scale. If pulse stacking can occur in one small pocket of space, how many more exist? How many spacecraft have missed these pulses because we weren't looking for them, or didn't have instruments sensitive enough to catch them? Could this explain other anomalies in cosmic ray detection on Earth, where background radiation spikes without cause? Are we seeing the tip of a much deeper pattern that spans the galaxy? Voyager 2 only has more signs and no answers. It keeps going through the dark in silence, recording rhythms, echoes, and data points that make us think more deeply about what we know. It wasn't supposed to work for this long, let alone find this strange beat in the void of space. Still, it is the first thing made by humans to connect to the deep, slow beating of space between the stars. Was something following Voyager? Voyager 2 was never meant to feel like it was being watched. It was launched to be a quiet scout that would move deeper into space without making a fuss or having anyone else with it. Then, something strange happened. Something small that was easy to miss at first, but impossible to ignore after it was seen. The data started to show reflections. Not light reflections like light hitting a mirror, but signal echoes. Voyager 2 sent radio waves into space, but they were being reflected back. Not all the time, not as expected, but just enough to make you look twice. This wasn't normal. Space is vast, empty, and cold. Once a signal leaves the spacecraft, it's supposed to spread out forever, unless it hits something, and that's where the mystery begins. These backscatter patterns, small, delayed versions of Voyager's own signals, were faint but real. Engineers initially chalked it up to Earth-based interference, maybe a reflection from a satellite? But timing ruled that out. The echoes didn't match any Earth-orbiting object's profile, and they only started occurring after Voyager 2 crossed into interstellar space. Next, they considered instrument error. Perhaps the high-gain antenna on Voyager was rebounding its own signal internally, but that would produce a consistent, short-delay echo. This wasn't that. These signals came with varying delays, some milliseconds, others much longer. Some even had slight frequency shifts, as if distorted by travel through different media. So then the team did what scientists always do. They ruled out everything they could. And what remained was this unsettling possibility. Voyager's signals were bouncing off something out there, something not listed in any star chart, something not glowing, not visible, not giving off any gravitational pull strong enough to notice, but something reflective and close. Could Voyager 2 be passing near or through an unknown interstellar object? A rogue cloud, maybe, a dense pocket of plasma, a dust shell from a long-dead star, or, and here's where things get spooky, a solid object, something with form, something capable of sending back a coherent echo. Just to be clear, no one is saying alien probe. That's always the last thing you think. But when every normal theory doesn't work, even the most cautious astronomers start to think about the unlikely. An area of bent magnetic fields, or a loose cluster of ionized gas that keeps its shape just enough to send Voyager's weak radio wave in a different direction, is more likely the cause. Or maybe a mini-magnetosphere, which is a space bubble with enough mass to send messages back. Small bodies in the interstellar space, like rogue comets or icy planetoids, could form these patterns around them, even if other sensors can't find them. Each time Voyager 2's signal echoed oddly, its particle detectors also noticed minor changes. Slight upticks in proton count, subtle magnetic twists, not enough to raise alarms but enough to say something passed nearby, or perhaps something lingered near the craft. There were echoes that seemed to move. One day, a signal came back with a 43 ms delay. A few days later, there was another bounce, but this time, it was 48 milliseconds later. That sounds like motion. Not from Voyager. It wasn't speeding up, from whatever the signal was coming from. Objects are moving when they change place. It changes if it's a field. Have the crew of Voyager 2 found a friend? A piece of matter moving in the same general direction, maybe caught for a moment by the craft's weak gravitational pull, or maybe even a piece of the sun's outflow, a magnetic echo following it through space. There's precedent for strange travel companions. The heliopore's electrostatic layer, an edge zone theorized to exist just beyond the heliosphere, may include lingering currents or boundary features that interact with outgoing signals. Voyager might be scraping against this boundary in ways no one predicted. Or it might have picked up a tail. Some scientists point to the possibility of reflected memory, that some of Voyager's transmissions hit denser regions of the interstellar medium and bounced back with delay, distorted like echoes in fog. But those echoes should scatter. They shouldn't preserve frequency integrity. Yet some of Voyager's strange signals came back eerily intact. You get scared when you hear things like that, not the big, strange, dramatic oddities, but the little things that should not be consistent. Whatever is really following Voyager 2 is not likely to be seen by us. There is no backward-facing camera on the tool. It sounds like a blind person whispering in the dark, picking up blips and strange events from a place no person has ever been. These changes in the signal may be the only way we'll ever know if something followed it or even just got close. Voyager 2 crossed into a region of unexpected stillness. Out in the farthest darkness, where even the sun's warmth is forgotten, Voyager 2 slipped into silence. This was not radio silence, but a real audible quiet in the space around it. The satellite had been looking for chaos, radiation bursts, particle gusts and plasma flows for decades before it suddenly reported nothing, or pretty close. No particles that surge, no waves in the magnets, not a shock. There was nothing but a flat line of quiet, which even NASA scientists agreed was strange. It wasn't just a glitch in the technology. The instruments on Voyager were fine. In fact, they were too steady. The magnetometer, the energetic particle tracker, and the plasma wave unit all picked up a calm that wouldn't break. Interstellar space isn't empty, at least in theory. Space rays, hydrogen atoms, rogue protons, and electromagnetic hum are some of the charged particles that are meant to be inside it. But signals dropped sharply as Voyager 2 went through this patch, the way a pond freezes over all of a sudden. Now, to understand why that's weird, consider what the spacecraft had already gone through. In the Heliosheath, just before breaking into interstellar space, Voyager 2 encountered a storm of plasma turbulence. It was like moving through a choppy ocean, with energetic particle levels fluctuating constantly. But past the heliopause, the border where the sun's influence wanes, scientists expected more chaos. The interstellar medium, far from being a serene vacuum, is usually jostled by distant supernova shocks, compressed magnetic fields, and rogue cosmic radiation. Instead, there was a peak, which was like the eye of the storm between the stars. Voyager 2 went through a region that had a steady plasma density, almost no magnetic activity, and no flares of cosmic contact. This went on for more than 20 million kilometers. This area is now called a null patch by some experts. We don't fully understand it, and it might not be the same everywhere. But it makes a strong case that some parts of interstellar space are more organized and strange than we thought. Instead of being a random mix of forces, the space between stars could have areas, layers, or even quiet pathways that were made by galactic shocks or long-dead stellar winds. A kind of interstellar stratification is an idea that is getting support. As supernovae remain and old stars throw off matter, they make rings and layers in the medium. It's possible that Voyager 2 wandered into one of those outer layers, where everything that could have caused chaos has already gone by, leaving behind a smooth, still space for a while. Another idea is that Voyager 2 stumbled into a magnetically shielded pocket. These can form when opposing magnetic fields compress and cancel each other out, much like a noise-cancelling headphone in reverse. That would explain the lack of particle interaction, since many cosmic rays ride magnetic flux lines to propagate. Scary, not because it implies danger, but because it suggests we know even less than we thought. Maybe we've completely misunderstood the structure of local interstellar space. Maybe it's not homogeneous. Maybe what Voyager found isn't a pocket, but the default. And what we thought of as the normal chaos of space is actually the exception, the echo of past violence still fading from nearby stars. There's also a timing angle. Voyager entered this still zone at the same time the Sun was undergoing a solar minimum, a natural cycle where solar activity drops, which affects even distant heliospheric boundaries. But the correlation doesn't quite hold up, because the Sun's declining activity shouldn't reach Voyager that far out. Still, the coincidence is noted. What's clear is that space isn't behaving like a smooth, expanding soup. It's acting more like a patchwork, turbulent here, quiet there, charged in one region, drained in the next. Voyager 2 didn't just pass through a physical boundary. It crossed into a new mood of the cosmos, one we didn't predict and still can't fully map. In terms of facts, there wasn't complete silence. Low-frequency plasma waves, those steady hums that point to deeper currents, were still picked up by instruments. Even those, though, seemed cleaner and had less background noise. It felt like Voyager was traveling through a cathedral-like vacuum, cold, quiet, and empty. NASA is still using the Deep Space Network to keep an eye on Voyager's signals. They haven't found a place like it anywhere else. No one knows if this calm is lasting, only temporary, or just a taste of what's to come in the deeper structures between the stars. The solar wind isn't slowing down correctly. At the very edges of our solar system, things should be slowing down. Physics tells us that. It's predicted that the solar wind, which is the stream of charged particles that the Sun sends out into space, will gradually weaken as it goes farther away. This is because the further it goes, the more it spreads out, and the weaker it gets. The idea comes from the inverse square rule, but Voyager 2 found something that doesn't make sense. As it approached the Heliosheath and crossed into the heliopause, Voyager 2's instruments began measuring the velocity and pressure of the solar wind with increasing precision, and what it found threw a wrench into decades of solar physics. The solar wind wasn't behaving like it was supposed to. Instead of smoothly losing energy as it pushed against the edge of interstellar space, the wind was losing strength in an uneven, inconsistent way. In some regions, it plummeted faster than the inverse square law would predict. In others, it flattened out, lingering at strengths far higher than expected, as if something was slowing its decline. It was like watching a wave crash onto the beach and then freeze mid-motion. The conventional model assumes the solar wind slows gradually as it collides with the opposing pressure of the interstellar medium. Think of it like two fluids pressing against each other, eventually balancing out. But Voyager 2's data showed spikes and dips in this transition zone. There was no clean handoff. The wind didn't just slow down. It twisted, decelerated abruptly, and sometimes even reversed slightly. Magnetic chaos is one of the most popular ideas. As Voyager 2 got closer to the heliopause, the supposed line where the solar wind ends and interstellar space begins, it is likely that it ran into areas with bent magnetic fields. These are like speed bumps that stop the smooth flow and make the solar wind behave in strange ways. Imagine going fast through a tube and hitting some rough air that you can't see. Not only does your car slow down, it jerks, bounces and loses speed in strange ways. Another possibility involves the existence of charge exchange regions. In these zones, high-speed solar protons collide with neutral hydrogen atoms from interstellar space. When this happens, they exchange electrons, transforming the fast-moving charged particles into slower-moving neutral ones. These interactions bleed momentum out of the solar wind, essentially stealing its energy, and they do it in pockets, not smoothly. That would explain why the slowdown is inconsistent. Some of Voyager 2's measurements suggested that the pressure gradient, the rate at which the solar wind's push diminishes, was inverted in a few spots. In basic fluid dynamics, this shouldn't happen. It's as if the particles were encountering invisible walls of resistance, then speeding up again after passing through them. Then, what could make that happen? Some scientists think that there might be interactions with huge magnetic loops that are fixed in the Sun's atmosphere. These loops are billions of kilometers long and finally collapse. If one of these loops moved outward and crossed Voyager's path, it could have caused a brief area of squished wind, like a traffic jam in space. However, this idea hasn't been proven, and models haven't been able to accurately repeat it. There's also the hypothesis of termination shock drift. The termination shock is the point where the solar wind suddenly slows from supersonic to subsonic speeds. Voyager 2 crossed this region, but instead of a clean drop, it measured a jittery, uneven collapse. This could imply that the boundary itself is unstable, shifting over time and space like a wobbly balloon surface. In this model, Voyager the 2nd of May have been sampling a highly localized version of the solar wind's behavior, shaped by microcurrents and pressure zones too subtle for models to currently capture. Some things don't make sense. This makes me wonder how well we really understand how the Sun and the world around it interact. The solar wind is not the only thing that shapes and changes the heliosphere, which is often thought of as a bubble around the Sun. It was shaped by cosmic rays, interstellar magnetic fields, and even the gravity of stars that passed by millions of years ago. The readings from Voyager 2 show that we may have made this system way too simple. The solar wind isn't a steady flow. It's a dance that changes over time in a much more complicated universe. And that means the slowdown of the solar wind isn't just about physics. It's a story of two worlds meeting. Our solar bubble brushing against the ocean of the galaxy. And in that collision, things don't always slow down the way we think they should. Magnetic walls confined the probe briefly. In August 2018, Voyager 2 did something strange that hadn't happened to it since it was first launched more than 40 years before. As the spaceship flew through an area that should have been pretty calm near the heliopause, the boundary between our solar system and interstellar space, the plasma sensors felt a sudden and strong increase in magnetic field strength. Not just a spike, ashes. For several hours, the data stream from Voyager 2 lit up with indicators that the magnetic environment around it had completely changed. The probe wasn't tumbling or malfunctioning, its instruments remained stable. But the magnetic field readings showed a massive increase in strength and directional coherence. It was as if Voyager 2 had driven straight into a magnetic brick wall. In classical astrophysics, this wasn't supposed to happen. The region outside the termination shock, between the Heliosheath and the interstellar medium, is theorized to be a turbulent mess. Plasma waves, fluctuating magnetic fields, and a whole lot of cosmic chaos. But walls, those belong in science fiction. And yet, that's exactly what Voyager 2 seemed to encounter. Scientists thought it might be a sensor artifact, a glitch, but then they checked Voyager 1's data. When it crossed the heliopause in 2012, Voyager 1 had reported a similar spike in magnetic field strength. Different instruments, different trajectories, different times, same phenomenon. That ruled out coincidence. Something real was happening at the edge of the solar system. A word that sounds almost magical was made up to describe it: the magnetic wall. It's just as scary as it sounds. The main idea is that the sun's magnetic field lines get squished together into a thin, thick layer as the solar wind slows down and presses against the medium between the stars. It's kind of like the bow wave that forms in front of a moving boat, but this bow is made of magnets instead of water. As Voyager 2 moved into this layer, the field lines got not only stronger, but also more organized. They didn't move around randomly. Instead, they lined up and gathered, making a kind of transparent barrier. Voyager 2 didn't just pass through this wall. For a brief window of time, it was trapped in it. The plasma wave subsystem, which listens for the ambient hum of charged particles, showed erratic behavior. Energetic particles seemed to bounce and jitter. For several hours, the flow of data was distorted, not lost, but agitated. Then, just as suddenly, the readings returned to baseline. It was as if the spacecraft had entered a magnetic bottleneck and then been released. But what could get a spaceship stuck in the middle of nowhere? It wasn't a machine. It wasn't caused by gravity. There was pressure in the field. A thick pocket of magnetic stress that can change how high-energy particles behave and stop a probe moving at over 15 kilometers per second. What's even more interesting is that this magnetic wall didn't change the spacecraft's path. It didn't push or pull it. It's just confined. Scientists who study the sun had to rethink long-held beliefs after learning this information. It's not just a fuzzy line where the sun's impact weakens. The heliopause is an active border with a complicated magnetic structure. It could make waves. It could fold. It could even hold charged particles in orbits that are almost stable, like magnetic eddies on the bank of a river. There's also the possibility that this wall isn't static. Instead, it could be a dynamic zone that shifts, grows, or contracts with the solar cycle. Every 11 years, the sun's magnetic field flips. That flip sends shockwaves throughout the heliosphere. So, what if the wall moves? What if the heliopause breathes? Another provocative theory is that Voyager 2's magnetic confinement wasn't caused by the sun at all. Some researchers speculate that interstellar magnetic fields, those belonging to the galaxy itself, could be pressing inward, shaping our heliosphere from the outside. In that case, the wall isn't our boundary, it's theirs. If these magnetic walls are common where stars meet, then our solar system isn't just a bubble floating through the sky. It's an electromagnetic object that sometimes interacts happily with the surroundings of the galaxy and sometimes not. The magnetic wall also makes us think about cosmic ray variation in new ways. During this confinement, Voyager 2 saw strange patterns in the high-energy particles that were coming in. Could these walls block out cosmic rays, or sound boosters? If so, they might explain why the amount of cosmic rays hitting Earth has changed over the years in ways we haven't fully understood. Finally, there's the scary part. There was silence on the wall. The trigger could not be seen. There was no storm. There was no radio burst. It just was. That moment was not only a strange science event for Voyager 2, but it was also a kind of liminal journey, a line that isn't made of matter but of force, of lines that can't be seen that are woven into the structure of space. A sudden drop in proton counts, then a surge. On July 8, 2019, something strange flickered across the sensors of Voyager 2. For a brief but unmistakable moment, its cosmic ray subsystem, specifically tuned to track energetic protons, recorded a sharp and unexplained drop. Proton counts plummeted, as if something had swallowed them whole. No warning, no cosmic event to blame. Then, just as abruptly, the numbers surged, rising to levels well above the previous baseline, like a geyser erupting in reverse. This wasn't how things usually work in space. At that point, Voyager 2 had already crossed into the interstellar medium. It was now traveling through an area that humans had never actually touched. It was clear what would happen. The farther away from the sun the protons would be. The particle count should have dropped slowly over time in interstellar space, following a pretty smooth curve. This rapid drop, followed by an unknown rise, went against every model in the book. To understand why this is such a big deal, you need to know how usual it is for protons to behave well. These very fast-moving, very energetic particles are mostly made by supernovae and other events in the galaxy. They are made up of stripped hydrogen atoms. They change with the activity of the sun close to Earth, but they should stay stable far away in interstellar space. Voyager 2 should have heard the dull, steady hum of protons in the background. It didn't get that. The data wasn't a glitch. The same instrument had been tracking particles for decades without a hiccup. Engineers cross-verified the readings with other sensors on board. Radiation detectors showed matching blips. Even magnetometer data recorded a subtle but measurable shift in the surrounding field, right around the time of the proton event. So, what caused it? One early theory suggested a shock wave from the sun, a coronal mass ejection, CME or solar flare, had finally reached Voyager 2 after traveling for months. But that didn't hold up. The timing was off. Other spacecraft between Earth and the edge of the heliosphere, like New Horizons, saw no such wave. If it were a solar echo, others would have detected it too. A limited interstellar event is another option. Voyager the 2nd of May have gone through a pocket of heavier cosmic plasma that had not been seen before, and that took in protons and then sent them back out again. Space isn't a sponge though. That's not how protons disappear and then show up again. A place with a lot of magnetic complexity would be needed to deflect, hold, and then release particles. This would be like having an unseen particle lens. That does sound strange, and it is. Even stranger is the idea that Voyager 2 went through a Null zone, which is a temporary empty space in the medium between stars where magnetic field lines cancel each other out. In that kind of place, high-energy particles might be temporarily stopped from moving easily because the directing fields aren't balanced. As the spaceship moved through the zone, the suppression would loosen, letting the trapped protons bounce back. The event itself is even more of a secret because it happened so quickly. The number of protons dropped over a period of minutes. The rise was the same. That's like slamming into a wall and bouncing back in space, where things change slowly over days or even weeks. Voyager 2 said there was no damage, no changes to the plan, no strange electricity things. There was a wave of quiet, and then there was noise. Some people think the probe may have hit the edge of a cosmic structure that no one knew about before. It's not a real thing, but a pressure limit. The cosmic medium isn't smooth in this case. It's bumpy, with spots that have different densities of particles. VOA could have gone from one bubble to another, like a diver breaking through an ocean thermocline. That doesn't fully explain the rise, though. The rise after the drop wasn't just a return to normal, it was higher than the starting point. It feels like something squished protons together and then let them go all at once. After a few hours, the spike went away and things returned to normal. Not the same as before, a little higher. No matter what Voyager 2 went through, it left a mark that will last. Could there have been a dark matter clash? Not likely. Since dark matter doesn't interact with protons through electromagnetic force, charged particle monitors wouldn't show a drop in the number of particles they find. Could it be an extraterrestrial magnetic field from something too far away to see? That's also not likely. Data on gravity showed that it didn't have any effect. What are we left with now? It's possible that this is the first proof of large-scale plasma patterns in space between the stars, the kind we haven't been able to find before because we haven't been out there. That's not all that Voyager 2 is. It's a particle tracker, a magnetic field analyzer, and a barometer for the world we live in every second of every day, but don't notice. This dip and surge of protons may not seem like a big deal in the big picture, but it's as loud as thunder on the quiet edge beyond our solar system. It means that the rules we thought controlled particles in space might only be true in our area. After that, we're finding out the hard way that space still has secrets for us. The cosmic ray tilt. As Voyager 2 moved deeper into space between stars, its instruments once again picked up something strange. We didn't see a quick surge of energy, a magnetic flip, or a strange plasma hum this time. It was less obvious. Not as fast, but just as strange. Cosmic rays are high-energy particles that come from outside our solar system. The angle at which they hit started to change. Not by chance, not in a crazy way, but at a planned slow speed that made scientists on Earth scratch their heads. Cosmic rays are a known quantity in astrophysics. They come from all directions, born in violent events like supernova explosions and black hole jets. These particles, mostly protons and atomic nuclei, travel at near-light speeds across the galaxy, and for decades we've known that when they reach our solar system, their paths are influenced by the sun's magnetic field. But out in the interstellar medium, that's supposed to be neutral ground, a place where cosmic rays roam freely, not bent or twisted by local forces. Except Voyager 2's data told a different story. Instead of an even isotropic distribution, meaning cosmic rays coming in equally from all directions, the probe detected a slow tilt. The particles were arriving from a preferred angle, and that angle was changing. Day by day, week by week, the cosmic wind was pivoting. Things like this shouldn't have happened. When the mission experts got back to Earth, they checked the cosmic ray module again and again. Was there a problem with the calibration? A problem with the sensor? After all these years, had Voyager 2 started to get worse at what it does? No was the answer. Everything was going well with the instruments. Voyager 1, which is very close to it but 1 billion kilometers away, wasn't really feeling the same thing. This ruled out a cosmic event that happened everywhere. Whatever was going on was close to where Voyager 2 was in space. Voyager 2 was going through a part of the galaxy where the magnetic field is bent or warped, according to one idea. Rays from the sun move along magnetic field lines like trains move along tracks. Things move in a circle if those tracks shift. But this would mean that the interstellar magnetic structure is a lot messier and more changing than we thought. The tilt wasn't a mistake. It kept going in the same way for a while, then changed. A little. Over time. We don't think the wind would do this. It looks more like Voyager 2 went under a ceiling fan and then into the wake of something else. A space jet stream, a tube of magnets. No model could have predicted this. Some scientists suggested that Voyager 2 had entered a coherent magnetic domain, a kind of invisible corridor in space where magnetic fields align over vast distances. In such regions, incoming cosmic rays would all be bent the same way, giving the appearance of a tilted distribution. But these coherent domains are theoretical, and Voyager's data might be the first direct evidence of their existence. It's also possible that Voyager went through the edge of an interstellar filament, which is a long, thin thread of gas or plasma with a higher density that is part of the bigger medium. People have seen these kinds of patterns in galaxies far away, but they have never been directly examined. In the event that they are real, they might bend and focus cosmic rays that come in from one side. That doesn't fully explain the slow change in slope, though. It looks like the area Voyager 2 was traveling through was rotating, like an unseen magnetic belt that was slowly bending space and changing the paths of the particles moving through it. Some people even thought that this tilt might be a side effect of something bigger, like a large-scale interaction zone between cosmic arms, or a ripple caused by the pull of a nearby huge object that can't be seen. Again, there isn't any real evidence, only strange data and ideas that keep going in circles. What makes this tilt especially significant is that it changes our baseline assumptions about cosmic rays. We've always treated them as a kind of background noise, coming from all directions, allowing us to measure solar activity, interstellar boundaries, and radiation levels. But if their incoming angle can shift like this, without any obvious cause, then they're telling us something deeper, something about the structure of space itself. And that leads to things. To go to deep space, for tasks that last a long time, to protect future space probes from radiation. If cosmic rays aren't spread out evenly, some parts of space might be safer than others. Some routes could be more dangerous for explorers or tools that are easily broken. This tilt might even change how we understand data from other satellites about cosmic rays. If direction and angle are more important than we thought, then our readings from Mars or Earth orbit might be missing important information. Voyager heard the universe buzzing. Voyager 2 found something haunting in the deepest parts of cosmic space, far away from the Sun's magnetic field. There was no voice, sound, or glitch. It sounded like a hum, a low buzz that wouldn't go away, a background plasma tone that they had never heard before, at least not this clearly. This one was steady, unlike the short bursts or wavy shapes that we usually see when there is action in the universe. Easy. It was like space itself was speaking. This buzz wasn't entirely unexpected, but the way it manifested was a surprise. Scientists had long theorized that the interstellar medium, the vast ocean of gas and plasma between stars, would carry some kind of vibration. After all, charged particles don't just drift in silence. They oscillate, they ripple, but most expected this hum to be chaotic, full of turbulence and noise from ancient supernovae, colliding gas clouds, or the distant echoes of stellar births. Instead, Voyager 2 picked up something unnervingly regular. It was a narrowband plasma wave signal hovering in the kilohertz range, just above the human hearing threshold. But when converted into audio by NASA's team, the result was eerie. A smooth, ghostly tone like a distant tuning fork ringing in an empty cathedral. It didn't stop. The plasma wave subsystem on Voyager 2 picked up this tone over and over from 2012 to 2020. The noise got louder at times. Sometimes it's softer, but it didn't go away completely. This wasn't a sharp plasma oscillation event like those that happen during solar flares or quick boundary crosses. It was the setting. It was a part of the medium. Scientists were even more confused by how stable the frequency was. Most of the time, plasma waves change depending on how dense and hot the air is around them. But in this case, the tone stayed in a narrow range, which meant that the medium between the stars, at least in this area, was more stable than predicted. Because the hum didn't sound like anything that comes from the sun. There was no sign of it coming from the heliosphere or the sun's outer sources. It was outside. And it seemed to say that the empty space between stars has a kind of music that we can't hear. A beat. Being there. The reason could be one of several. One has to do with electron-plasma oscillations, which happen when free electrons in a plasma field bounce around a neutral point together, making a tone that resonates. That's most likely part of what Voyager 2 saw. That doesn't explain the consistency or perseverance, though. It's like hearing a violin note that should go away, but never does. Could this buzz be part of a galactic plasma network? Some researchers believe so. The Milky Way is laced with magnetic filaments, some stretching for hundreds of light years. These could serve as cosmic waveguides, carrying and amplifying certain plasma frequencies. If Voyager happened to pass near one, that might explain the clarity of the tone. Others think the buzz might be a leftover from when the galaxy was being formed, a type of galactic background noise that was left in the space between the stars billions of years ago. Voyager didn't just hear a random plasma tone if what they say is true. It heard the past, a whisper from the past that didn't go away. Some propose that the buzz could be modulated, altered subtly in ways we haven't yet detected. In other words, it might carry information, like Morse code embedded in a drone. There's no hard evidence for this yet, but some researchers are running the data through machine learning models to detect patterns the human ear and eye can't perceive. In addition to being natural, some people have said that this sound could be used as a beacon to find safe areas in interstellar space. Birds use magnetic fields to find their way. Could future probes or even alien species use plasma hums to find their way? It's not just the sound of the Voyager 2 buzz that's strange, it's what it means. A warning that the world is always sound, even when it seems to be quiet. There's always a flow, a sound for the background. Voyager 2 captured a moment in this endless song, a fragment of galactic ambience we didn't know we could hear. And now, thanks to that aging probe speeding through the dark, we know space isn't empty, it's resonating. It might look like this hum is very small, just a line on a frequency map, but it's a powerful warning that there are things around us that we don't fully understand. Voyager did more than just look into space. It paid attention. What it heard was strange, beautiful, and living in a strange way. Voyager entered a field with forbidden frequencies. Voyager 2 went deeper into interstellar space, past the heliopause and into the unknown. As it did so, it found frequencies that, according to what we know about physics, shouldn't be able to travel through space. Some experts have called these frequencies forbidden. They didn't come in a single clean packet. Instead, they were spread out over several broadcasts and showed up as splinters in scans of plasma waves that were otherwise normal. The tools were working properly. It wasn't noise. It was clearly a signal, repeating, measured and real. Electromagnetic waves travel through space based on well-established laws. In a vacuum, waves above a certain frequency tend to attenuate less, while lower frequency waves, especially those below a few kilohertz, get lost in the plasma background or can't travel far without a medium. But what Voyager 2 found were spikes at frequencies far outside this normal propagation band, in some cases dipping into regions previously thought impossible to sustain over interstellar distances. These weren't just rare blips. Over time, the spacecraft recorded a persistent presence of extremely low frequency waves that required a denser or differently composed medium to sustain their amplitude. But the space just outside the heliopause, where these signals were recorded, is considered one of the most tenuous environments known. Particle density is lower than anywhere inside the heliosphere. There should be less structure here, not more. And yet, the data shows something defying that emptiness. One possible culprit is the presence of unknown structures in the interstellar medium, filaments, pockets, or walls of gas and dust with unusual electromagnetic properties. If such regions existed, they could potentially act as waveguides or resonant cavities, altering how electromagnetic radiation moves. This would make sense if the spacecraft passed through one such structure and briefly picked up scattered or amplified signals. But it's not just a matter of weird material properties. Some frequencies logged by Voyager 2 dip into ranges below the plasma frequency of the surrounding environment, a theoretical limit that dictates the minimum frequency at which electromagnetic waves can travel through plasma. Below that limit, the wave should simply reflect or be absorbed. Instead, Voyager recorded them as if the medium was transparent. The consequences are important. If the plasma frequency barrier can be broken, it means that our ideas about how space, especially cosmic space, works at the microphysical level may be off. This could change everything from how we learn about cosmic radiation to how we find faraway events like gamma-ray bursts or even signs from other galaxies. The most conservative explanation is a previously unknown interference effect. Perhaps these frequencies are being generated by interactions between cosmic rays and dust, or by magnetic reconnection events happening far from the spacecraft. But even in those scenarios, the coherence and repetition of these waves is hard to explain. These weren't stochastic noise signatures. They followed patterns, implying an organized source. A different idea that is becoming more popular is that Voyager 2 accidentally entered a region of nonlinear plasma interaction. In these places, different waves can join in ways that make new frequencies appear, just like mixing sound waves can make beat frequencies in music. These combined waves might not be moving through space the way waves usually do. Instead, they might be riding the local magnetic field lines in ways we don't fully understand yet. The other type of idea is more speculative and has only been talked about in physics groups and not in peer-reviewed papers. What if these frequencies that aren't allowed are caused by quantum vacuum changes that get boosted on very large scales? In that case, Voyager is picking up the mark of quantum activity on the structure of space itself. These are ripples in the fabric of space-time that can be heard because of plasma. Of course, it's also possible that we're just not equipped to explain what Voyager 2 is detecting. We designed its instruments based on our best understanding of the universe in the 1970s and 1980s. That it's even functioning in 2025 is a miracle in itself. Perhaps these anomalous frequencies are the beginning of a new branch of plasma physics, one we never knew we'd need. It's not enough to just learn that space is weird. It's that our ideas are only temporary. The Voyager 2 data has always made us change, improve, and sometimes throw out our beliefs. There are songs we haven't learned to hear in the vast, cold, and seemingly empty space between the stars. This is what the forbidden frequencies tell us of. The plasma was too hot. From every textbook, model, and program, Voyager 2 should have gone into a cold place when it crossed into interstellar space in November 2018. It's not just cold, not just cool, deeply, darkly, almost unbearably cold. This is space that is not affected by the sun or the solar wind. There are few particles and little energy in this space. Voyager 2 instead found something strange. The plasma, beyond the heliopause, wasn't cooler, it was hotter. This wasn't just an instrumentation glitch. NASA engineers cross-checked, recalibrated, and verified. The data was solid. And the numbers? The interstellar plasma temperature measured by Voyager 2 was higher than the surrounding solar wind plasma it had just exited. In some cases, it clocked in at over 50,000 degrees Kelvin. That's hotter than the surface of the sun. To be clear, plasma isn't the same as the air we breathe or the heat we feel. It's a soup of charged particles, ions and electrons, so diffuse that you'd find fewer atoms in a cubic meter than you would in the emptiest vacuum chamber on Earth. Yet even with such low density, the thermal energy, how fast those particles are zipping around, was significantly greater than expected. So much so that it caught physicists off guard. What's making it hot? One idea says that the solar wind and the space between the stars interact with shocks. The heliosphere, which surrounds and protects our solar system, is like a fast car driving through a storm. The rain doesn't just break up around the car, it pushes against it, splashes, and stirs things up. In the same way, when the sun's wind hits the gas between the stars, it may create a shock front, which looks like a loud boom and burns the material that comes in. But this comparison isn't quite right. Models that are based on this idea still can't explain how big the heat was that Voyager 2 saw. Magnetic reconnection is another option. This is when tangled magnetic field lines snap, readjust, and release bursts of energy. It has been seen close to Earth, in solar flares, and in the corona of the Sun. When the Sun's magnetic field reacts with the interstellar field, the same thing could happen, releasing areas of high heat energy. But once more, the warmth is consistent and large, which suggests that it is more than just a few random magnetic bursts. There's also a theory involving turbulence in the interstellar medium itself. Though we often think of space as static and dead, it's anything but. The interstellar medium is constantly stirred by the remnants of supernovae, by the winds of distant stars, and by gravity's quiet pull. This turbulence might cascade energy down into smaller and smaller scales, heating particles in a way that current models don't account for. Some have even suggested that micro-instabilities in the plasma, invisible to our satellite's crude instrumentation, might be generating heat through wave-particle interactions. Could dark matter be interacting with each other? It's possible that we're coming up against areas where the density of dark matter slightly rises, affecting normal matter in ways we don't fully understand through gravity pull or even direct interactions. However, there is no proof for this at this time. The door will open when normal physics fails. Then there's the idea that no one wants to be true, that our knowledge of interstellar space and plasma physics at these sizes is just wrong. It's possible that Voyager 2 is telling us that an important piece of the puzzle is missing, something about how energy moves in harsh conditions. There is something that hasn't been seen because no other spaceship has been this far out with equipment that can find it. What makes this all even stranger is the comparative data from Voyager 1. While both probes crossed into interstellar space, Voyager 1's plasma instrument failed decades earlier, forcing scientists to infer plasma density indirectly via magnetic and particle data. Voyager 2, however, had a still functional plasma wave subsystem, providing real measurements. That means this discovery, the heat that wasn't supposed to be there, is new, unfiltered, unmistakable. What's the bigger point? Space isn't all the same, and our ideas about how cold it is might not be true at very large distances. It's possible that the world is not as cold as we thought. There may be energy hidden in strange places, like hot plasma areas floating in space that are powered by forces we haven't called yet. This one anomaly unravels a lot. If interstellar plasma is hotter than expected, it means models of cosmic ray propagation need to be updated. It affects how we understand the shielding potential of the heliosphere. It may even play a role in astrobiological considerations, because high-energy plasma behaves very differently in the presence of organic molecules. We've learned something very important from Voyager 2. The edge of our solar system is not a wall, a drop-off, or a quiet fade to black. It's an oven, a place with a lot of energy, movement, and conflict. The more we go, the louder the world seems to scream that it doesn't want to follow our rules. The magnetic field has a grain. We usually picture smooth, beautiful arcs, gentle curves that move charged particles in big, unseen loops when we think of magnetic fields in space, especially in the void between stars. That picture was broken, though, by Voyager 2's sensitive magnetometer. Beyond the heliopause, the magnetic field between the stars wasn't smooth. It wasn't smooth. It had a lot of structure and almost a pattern, like space itself had a cloth. That wasn't meant to happen that way. Most models of astrophysics say that the magnetic field in interstellar space should be like a stretched-out rubber band. It should be calm over very large distances, with only small waves caused by shock waves or moving clouds of gas. But Voyager 2 saw sudden changes in direction, uneven strength gradients, and fluctuations that were not lined up in a normal way. It looked like the field had seams. This discovery wasn't a simple calibration error. Voyager's twin magnetometers, mounted far from the spacecraft's core to avoid interference, had been meticulously tested. And this wasn't a one-off event either. Over thousands of hours of readings, Voyager 2 kept seeing the same thing. The magnetic field wasn't smooth at all. Instead, it varied sharply over distances, as short as 1 astronomical unit. That's the distance between Earth and the Sun. Imagine you're walking across a room expecting a flat hardwood floor, only to discover hidden grooves and dips beneath your feet. That's the level of surprise here. The magnetic field didn't just gently change direction over time, it jittered, as if space had layers or boundaries or microscopic currents pushing back against one another. What then could be causing this? It's possible that the gap between the stars moves around more than we thought. Localized turbulence or areas of heavier gas could tangle and twist magnetic lines, adding knots and eddies that look like texture. The field would act like a river running over rocks. It would be wild, foamy, and always moving. Another explanation involves magnetic reconnection, the violent rearrangement of magnetic field lines that releases energy, often seen on the Sun. In interstellar space, if reconnection is happening frequently, it could leave behind residual structures, like scars, that imprint patterns into the field. These residuals could persist for thousands of years, creating that grainy texture Voyager 2 felt. Some experts believe that explosions may be to blame. A huge star doesn't just blow up a cloud of gas, it also sends shockwaves that can bend, twist, and ripple magnetic fields over thousands of light years. Over time, these ripples may blend together to make a woven design that is hard to see, unless you're in space and going straight through it. Others suggest the texture may be a consequence of how the Sun's magnetic field interacts with the galaxies. As the solar wind pushes outward, it warps the magnetic lines of the interstellar medium, creating turbulence. Picture two weather systems colliding in Earth's atmosphere. Storms, shear, and unexpected flows emerge. Now imagine that interaction on a scale spanning trillions of kilometers. The grain might just be the friction zone between these two titanic fields. What if this texture isn't just a result of ordinary plasma physics? Some researchers propose that what Voyager detected might hint at quantum-level interactions, or even relics of the early universe. In some models of cosmic inflation, small anisotropies, directional differences, were imprinted into the very fabric of spacetime. If true, these would show up as subtle alignments or granular distortions in the magnetic field billions of years later. And here's Voyager 2, maybe brushing against one. This idea gets even stranger when you consider that cosmic microwave background studies, like those from the Planck satellite, have hinted at unexpected large-scale alignments in the universe. Could Voyager's local data be detecting a much bigger pattern, something cosmological in nature? If space has a texture, meaning it's not completely smooth, then the way we model plasma activity at gaps between stars might need to be changed. Our present models are based on the idea that statistics are the same over long distances. However, that consistency is only a trick if the magnetic field has layers, folds, and directed grains. This would also change the way we think about how particles move. For example, magnetic fields help cosmic rays move. If those fields aren't smooth, the high-energy particles would scatter in different ways, which could change everything from statements about radiation shielding to basic ideas about how particles are spread out in the universe. It even impacts communication. One idea floated by scientists is that this magnetic grain could scatter or refract low-frequency signals in subtle ways. If we're ever sending spacecraft even deeper, or trying to receive faint whispers from distant stars, these structures could be a kind of cosmic fog we've never accounted for. Voyager 2, which went farther from the Sun than any other working ship except its twin, showed us something we didn't even know to question. The space is not blank, that the field doesn't have anything in it, that the space between the stars isn't just empty space, but is held together by patterns we can't see yet, but are starting to understand. The instrument that read the same value for 12 days. Every reading on Voyager 2 is important. There are more than 130 astronomical units between each piece of data and the edge of the solar system. That's more than 20 billion kilometers. So when one of its tools kept giving back the same number for 12 days in a row, scientists back home were torn between two options. Either something was broken, or there was something out there keeping that number steady. It wasn't only noise. The low-energy charged particle device on Voyager, which is meant to track ions and electrons in space, started sending a stream of data that was totally flat in one of its channels. Not just values that don't change, but numbers that don't change at all. There was no small change, not a rounding mistake. The reading was pretty much set in stone for almost 2 weeks. In deep space physics, that's not normal. Even in stable environments, there's always some degree of variation. Cosmic rays ripple, magnetic fields shift, plasma densities evolve with time and position. The idea that nothing changed, not by a fraction of a digit, was absurd. Engineers were quick to check for a malfunction. Was the sensor frozen? Was the memory register stuck? Could thermal expansion or deep space cooling have jammed a mechanism? But diagnostics didn't support that conclusion. The instrument was responding correctly to internal test pulses. It just wasn't seeing anything different. Voyager 2 had entered a part of space that was so regular that the sensors didn't find anything new. Plasma scientists didn't understand this idea. Even when it's empty, space isn't still. Cosmic rays from the galaxy can get in from any direction. Magnetic fields change. Even though the solar wind is weaker now, it still has an effect on things far beyond the heliopause. But there was a device that showed that all of those effects were no longer present for 12 full days on Earth. According to one idea, Voyager went through a null zone. This is a pocket of the interstellar medium where charged particles are spread out evenly, possibly because of a rare magnetic cancelling. If several field lines are exactly at odds with each other, they can stop local changes and stop particles from moving. Basically, a space-dead zone. Another possibility points to magnetic mirroring. If Voyager 2 entered a corridor of magnetic lines that were tightly aligned and symmetric, it's possible that the charged particles simply couldn't enter. They'd bounce off the edges, trapped by the geometry, leaving Voyager inside a magnetic cavity, silent and untouched. A more exotic suggestion involves ancient supernova remnants. If Voyager had passed through the diluted outer edge of a very old supernova shockwave, the remnant plasma may have reached thermal and energetic equilibrium long ago. That would explain the eerie stillness, a place where all particle motion had balanced out over millions of years. After 13 days, the number went up. Not over time, not step by step, just snap. There was a sudden change, like Voyager had crossed an imaginary line. The value went up and stayed at the new level. Things went on normally as if nothing strange had happened. There seems to be a border between these things, something sharp, narrow, and organized in space. Right away, scientists linked the event to well-known limits in the heliosphere such as the heliopause and the termination shock. That said, Voyager had already gone by those. What did this mean? It could have been an interstellar current sheet, a thin layer where the direction of magnetic fields suddenly flips and particle behavior changes dramatically. These sheets, though theoretically predicted, are incredibly difficult to observe. Voyager 2 might have just flown through one of the rare, dense ones. Many people thought about how a rogue object might affect the Earth's gravity. It's possible for a small mass, like a comet core that got lost or a dark object, to change the local magnetic field and particle flow without being noticed. Not enough to be seen directly, but just enough to change for a short time the plasma world around Voyager. As soon as it was over, the numbers went back to being normal. Long-term impacts on the area were not possible because the event had a sharp edge. It wasn't the Heliosheath, which is many thousands of light years across. It was more like Voyager slipped through a doorframe without being seen. What the flat reading really meant is even stranger. Was there really no change because there were no particles? Or was it just a perfect balance of energies that didn't interact with each other? Did Voyager happen to pass through a place where time, motion, and field action were all frozen in place? The raw info is still being looked at right now. Voyager 1's path has been used to rewrite, compare, and cross-check models. But nothing like that has been found on its twin's journey. This stalled sensor event might be one of a kind. If it is, it could lead us to a new type of structure in deep space that is brief, unseen, and perfectly uniform. Gravitational lensing. From what? In the usual sense, Voyager 2 wasn't meant to see anything. It doesn't have a camera that can focus on stars or a lens that can see galaxies. It's a spaceship made to measure magnetic fields, plasma fields, and particle streams. But something strange happened to its data at some point as it slowly drifted into space between the stars. The simple expected signs began to bend. That really shouldn't have been possible. It looked like gravity lensing was happening. A large object, like a star or black hole, bends the space around it, which makes light or radio waves curve. This is a well-known effect in astronomy. We've seen it from Earth and even used it to find galaxies that are hidden behind other galaxies. But Voyager 2 was in empty space, a long way from any known stars or planets. So when its data showed that some outgoing messages were arriving at Earth late, messed up, or slightly off in frequency, the only question that made sense was, what the hell was out there? Engineers first considered internal error, maybe a timing malfunction, a software glitch, or thermal stress caused the signals to wobble. But those were quickly ruled out. The instruments had operated flawlessly just prior and resumed normal behavior afterward. The anomalies were isolated, brief but undeniable. It was as if Voyager's signals had brushed past something invisible and massive, something with just enough gravitational pull to bend them slightly, like a magnifying glass distorting an image. Not enough to scramble the data, but enough to nudge the timing. The effect was faint but measurable. This opened up a crazy possibility. Something with an unknown mass went by between Earth and Voyager 2. What kind of object, though, could cause gravitational lensing that weak that no telescope on Earth could see? It could be a brown dwarf or rogue planet, which are cold, dark, and hard to see. These failed stars are out in the sky, not lighting up any solar systems. Someone or something could have changed the broadcast direction if it had been in Voyager's line of sight. Another theory points to dark matter clumps. These hypothetical concentrations of non-baryonic mass could exist in small halos, perhaps no bigger than a moon, but with enough density to warp space. If Voyager 2 intersected one of these halos even for a short time, the bending of space could mimic the lensing effect, without any visible object ever appearing. The even stranger possibility is that black holes were there from the beginning of time. If these were real, these leftovers from the Big Bang would be very small. Maybe not even a city block, but very thick. We've never seen one. But they're one of the few possible kinds of dark matter that could exist. The signal bending would be real if someone sped past Voyager's path, but it can't be found today. The lensing wasn't just observed on one transmission. There were multiple events over a span of several weeks, not all from the same direction, not all with the same characteristics. It wasn't a one-time flyby. It looked like Voyager might be sailing through a turbulent corridor of warped space-time, where these effects randomly flared up and vanished. Some physicists speculated about gravitational waves, ripples in space-time caused by massive cosmic events. But Voyager 2 lacks the sensitivity to detect them directly. Yet, if a low-frequency gravitational wave passed through that region, it could subtly affect the geometry of space, just enough to tweak the signal path. But the math didn't quite add up. The changes that were seen were too organized and consistent. The noises weren't just random. The thing that caused the displacement had limits, edges. It might even have its own gravity field. Now we can talk about the idea of a gravitational lensing bubble, a structure in which mass isn't needed, just the bending of space-time. It's possible that these bubbles are caused by strange energy left over from inflation or quantum shifts. Light would bend in this kind of bubble. Time would slow down. You never know, Voyager might have gone right through one. Of course, there's no direct proof. Voyager 2 didn't capture an image of a black hole or tag a wandering planet. What we have is timing drift, frequency distortion, and a consistent pattern across multiple transmissions. Enough to raise eyebrows. Enough to rewrite a few paragraphs in heliophysics textbooks. However, it is possible to explain what it isn't. Scientists looked over the Doppler data for hours and compared it with antennas on Earth. They even checked it against Voyager 1 to see if there were any patterns that were the same. But Voyager 1 was going in a different direction and was a long way from the area where Voyager 2 was making readings. There were no errors in the matches. Not the whole universe, just this one area, certain and short-term. This brings us to the last and most unlikely possibility. Voyager 2 saw more than just gravitational lensing. It also saw a secret structure in outer space. Voyager may have brushed against a rogue cloud. Voyager 2 was supposed to be able to sail through quiet, but all of a sudden it was in rough seas. Not the kind of turbulence that makes things shake and jump. This was particle level, unseen and very strange. Voyager 2 went billions of miles into the coldest part of interstellar space, and then entered an area where the particle density suddenly and wildly increased for no clear reason. No source could be seen. There was no change in the path. There was something out there, though, and the most plausible explanation: a rogue molecular cloud. Molecular clouds are the nurseries of stars, dense, cold regions filled with gas and dust. They're massive structures in galaxies, often light years across, glowing faintly in radio and infrared. But what if a smaller, darker cousin exists, one that doesn't emit light? One that drifts aimlessly through the void? One that Voyager 2, by sheer accident, skimmed the edge of? The first hint came from Voyager's plasma instruments. The particle detector showed a sudden rise in neutral hydrogen and heavier ions. These weren't solar wind leftovers. Voyager had long passed the heliopause, the outermost boundary where the solar wind gives way to true interstellar space. These particles were colder, denser, and moved differently. Their energy signature didn't match what scientists expected for that part of the interstellar medium. It looked like Voyager had gone through a mist in space. The time was even more interesting. The spike didn't happen slowly, it happened all at once. It took several hours for the density to rise, reach its peak, and then fall. That's way too short for an event that big of a size. We would have thought that the density would stay high for days or even weeks if Voyager had come across a bigger molecular cloud. It wasn't a deep dive, though. It was just a skim. A close call, a cosmic switcheroo. That's why researchers proposed a rogue cloud, possibly a fragment of a larger structure, broken off eons ago and wandering alone. It would be dark, invisible to telescopes, and impossible to detect until you were right inside it. Voyager 2 might have just grazed the edge like a boat slicing through fog along a hidden shoreline. But that makes me wonder how common rogue clouds really are. Why haven't we seen them before? The answer might be in how they are put together. If the cloud was mostly cold hydrogen with very small amounts of dust, it would not show up on most scans. It could be missed by radio antennas. If there was no heat source inside the cloud, infrared would not be able to see anything. Even gravity wouldn't have much of an effect. It would be too small to bend light or change paths in a way that could be seen. To put it another way, these things might be everywhere. Voyager 2's encounter wasn't just a curiosity, it was a possible first contact with an entirely invisible population of interstellar structures. Another clue came from the magnetic field data. As Voyager passed through the dense region, the surrounding magnetic field lines fluctuated. They weren't just perturbed, they twisted and tangled slightly, as if being dragged or redirected by something with mass and magnetism. Not enough to alter the spacecraft's course, but enough to change the shape of the local field. This effect matches what we'd expect from interstellar clouds. They don't just contain gas, they interact with the galaxy's magnetic scaffolding. If Voyager brushed a magnetized cloud fragment, the distortions in its readings would make perfect sense. Skeptics, on the other hand, offer other theories. Some people think the density spike was either a problem with the instruments or a delayed solar event that got through the heliopause in some way. They don't hold up under close examination, though. The instruments on Voyager were working properly. Earth-based telescopes and Voyager 1, which went in a different direction, did not find any action on the Sun that matched it. There is still the creepy chance that Voyager 2 found something that wasn't meant to be there. Many possible ideas are brought up again by this meeting. Could rogue clouds be made from the remains of star systems that have failed? Could they have small amounts of organic molecules or even prebiotic materials? Are there seeds all over the universe? Have they been around for billions of years and cooled down? Are they leftovers from when the universe was young? If there are more of these clouds than we thought, they might show a secret change in the way the galaxy works. Not just inactive floaters, but active players who move between systems, change the chemistry between stars, and maybe even send the building blocks of life over unimaginable distances. The timing glitch that matched a distant quasar pulse. Time is very important in the very quiet place. Voyager 2's internal clock is used to time data bursts, figure out what cosmic events mean, and keep track of how far away it is getting from Earth. But one day, that accuracy broke down. Voyager 2's internal clock moved, showing a small but detectable change. If it had been by itself, it might have been written off as old technology. That's not all, though. It happened at the same time that a quasar far away sent a strong pulse towards Earth. The quasar in question, known to radio astronomers for its rhythmic, high-energy pulses, emitted a sudden outburst that was picked up by observatories back home. These types of emissions are intense, high-frequency beacons from supermassive black holes at the centers of ancient galaxies. They're loud, far-reaching, and nearly timeless. Yet somehow, Voyager 2's timing systems jolted precisely when that flare was recorded. Now, spacecraft clocks aren't supposed to care about what quasars do. Voyager 2 is hardened against cosmic rays, shielded from ordinary fluctuations, and continuously monitored for calibration. So why would a quasar, billions of light-years away, seem to echo inside the circuits of a lonely spacecraft? Scientists have thought that electromagnetic interference, but not the kind we'd expect close to Earth, could be to blame. If the pulse from the quasar was boosted by lensing or alignment, it could have hit the right note, a sound wave, a burst of strange energy that briefly got past Voyager's shields and messed with its systems. Another idea has less to do with force and more to do with chance. Could it have just been the stars aligning? A light wave that's billions of years old showing up just as Voyager's systems that are decades old start to fail? Maybe. But the odds are thin. The pulse and the glitch were recorded with near-synchronous timestamps. The delay between the quasar pulse's arrival on Earth and Voyager's anomaly, adjusted for distance and light lag, was eerily close. The mistake in timing didn't hurt anything. Voyager 2 didn't restart, stop, or act differently. The clock went off at odd times, but it fixed itself after a while. It looked like it knew it had closed its eyes. This event adds to the growing list of strange things that mission experts have seen. There may never be a full answer. It could just be a coincidence. Or it could be a sign that even the empty, cold space can have resonances that come from nowhere, echoes from a long time ago, hitting old gear and leaving the tiniest ripple. Voyager detected neutrino-like ghost signals. There are particles in the universe that don't interact with anything much. They don't interact with matter, light, or even the strong magnetic fields that twist through galaxies. Neutrinos are their name, and they move through space like ghosts, almost impossible to see or catch. But during a strange part of its trip, Voyager 2 picked up signals that looked like ghosts and didn't match any known charged particles. It started with minor disturbances in Voyager's onboard particle detectors, tiny, unexplained blips in the data. Normally, these instruments record charged particles like protons or electrons, or they pick up on known types of radiation. But this time, there was nothing to account for the triggers. No accompanying plasma burst, no solar flare, no cosmic ray spike. Just subtle pulses, weak, quiet, and completely outside the normal patterns. Engineers first assumed these were just static noise caused by the aging of Voyager's hardware. After all, the spacecraft is more than 4 decades old. It's a miracle it's even still sending usable data. But when analysts lined up these anomalies with magnetic field measurements and local plasma densities, something strange became clear. These ghost signals tended to occur in regions of high spatial distortion, areas where magnetic fields bent unnaturally or plasma flows acted strangely. That's when the neutrino idea was first put forward. Voyager 2 wasn't made to find neutrinos, though. There is no NASA ship in deep space that is. If you want to catch one, you need huge buried monitors on Earth that are filled with thousands of tons of water or ice. But it's possible that Voyager's instruments might move if a neutrino or something like it had enough energy or interacted in just the right way. Not in a clear, measurable way, but in a creepy, quiet way. If these were neutrinos, they weren't coming from the sun. Their energy was too erratic, and the timing didn't line up with any supernova remnants or gamma-ray bursts. They were just there, floating through the silence, and that alone is weird. These were even stranger than neutrinos. In advanced physics, particles called sterile neutrinos or dark photons have been thought of as strange particles that don't interact with anything in the world we know of. Voyager the 2nd of May be the first ship to find a place where these particles actually left a mark. It is currently sitting still in the void. NASA never really called them ghost particles, though. However, several researchers have said in private talks and studies that these findings don't quite fit with what we've seen before. It wasn't normal radiation, no matter what caused the results. Solar wasn't it, and it didn't act like anything else Voyager 2 had seen or heard before. That leaves us with one more puzzle on the edge of what we know. Voyager entered a zone where light behaves differently. Light's only job is to move through space at a steady speed in straight lines. Because of gravity, it only bends near very heavy things like stars or black holes. That's what we can learn from general relativity. That's what makes our telescopes work. But as Voyager 2 moved deeper into interstellar space, its devices started to pick up something that didn't make sense. Radio waves and photon-based signals were acting in a way that wasn't quite right. The Voyager probes don't carry cameras anymore, but they do rely on light, radio light, to communicate with Earth. These radio signals are precise, clean, and predictable. But for a brief period during its journey, Voyager 2's returning signals were bent. Not delayed, not lost, bent. Engineers at NASA's Deep Space Network noticed the phase shift. Something had ever so slightly refracted the signal. Not the sun, not a planet, not a known object. There was nothing in the probe's line of sight to explain the change. In theory, if a gravitational lensing event occurred, the bending of light should correlate with a known mass. But Voyager wasn't near any stars. There was no gravitational source. The distortion wasn't sharp or dramatic, just enough to raise eyebrows. The signal seemed to wobble, like a laser beam passing through heat ripples. Except in this case it was cold, empty space. Could dark matter be to blame? That was one hypothesis. If Voyager had unknowingly drifted through a dense clump of dark matter, something that doesn't emit light or interact with it, it might still bend the path of photons with its gravity. But such clumps should have other gravitational signatures, and Voyager's instruments detected none. An electric oddity was another idea that was put forward. Radio waves could be distorted by plasma waves or cosmic dust, similar to how Earth's ionosphere changes messages from satellites. But once more, the plasma data during the distortion were normal, so there was no reason for the distortion. Some thinkers came up with the scariest idea. The structure of space-time in that area might be different. Quantum physics says that the world is not flat. It's thought to foam or change to very small sizes. It's possible that Voyager went through an area where the foaminess got big enough to change real, large-scale light courses. If that's true, Voyager the 2nd of May have passed through a space-time distortion, one not caused by mass, energy, or any known force. Just a wrinkle in the fabric, a region where light doesn't move the way it should. What made this discovery more chilling is how fleeting it was. The anomaly didn't last long, a few hours maybe. Then Voyager's signals snapped back to normal. No lingering effects, no explanation, just a cosmic shrug. The hardware wasn't broken, the experts did the checks. And Voyager 1, which is like it, never had the same problem, at least not at the same distance. No matter what Voyager 2 hit, it was only found in that one place. If light can bend in empty space where there is no gravity, then optics and relativity might not always be true. It makes me think that there are places in the world where our rules don't apply. Hidden places where light acts strangely and physics isn't clear. The bizarre discovery, physics broke at the edge. Physicists were shocked and stared blankly at their screens, not sure if they were seeing a mistake or the start of a paradigm shift. Voyager 2 had crossed the heliopause, which should have been the last known boundary. It was now more than 12 billion miles from Earth. After that, it went into interstellar space, which is the big, cold, quiet space between the stars. In late 2018, As Voyager 2 passed beyond the heliopause, its plasma wave instrument, an aging but still functional device, began returning measurements that shocked NASA. Instead of finding a thinning sea of cold particles, Voyager detected increasing plasma density, higher than expected, rising faster than any current model could explain. At this point, physics didn't seem to work anymore. This wasn't how the plasma outside the heliopause was meant to act. Our understanding is that solar particles get less dense as you move farther away until the interstellar medium takes over. The data from Voyager 2 showed the opposite, though. As the spaceship moved farther away from the Sun, the particles got denser, which means they had more energy. Why would space between the stars get heavier as you go farther away? Scientists were rushing to find answers. Some people thought Voyager had entered a type of boundary layer, which is a ring of cosmic matter that is squished together by the Sun's wind. It didn't work out, though. The population stayed strong well past that made-up zone. Others believed the ship may have passed through a local cloud of material, which was a warm interstellar cloud made of partly ionized hydrogen and helium. It should have been clear from scans of dust, magnetic fields, and particle flows, though, if that were the case. It wasn't. What made this even stranger was that Voyager 1, which is identical to it, had gone into interstellar space 6 years earlier, but in the opposite way. It also said that the plasma levels were higher than expected. Not like this. Voyager 2's readings were much more dramatic, lasted longer, and didn't fit with any known models of the medium between the stars. This wasn't a repeat. This was something else entirely. Some fringe theorists proposed we were seeing the outer edge of a hidden structure, a kind of interstellar sheath that wraps our solar system. If true, it might mean space has layered zones of differing physics, like strata in rock, and Voyager 2 had pierced a new one. Some experts were even more daring and thought that these results might mean that the usual ideas about how vacuums behave don't work after all. Could there be big changes in the density of the quantum vacuum? Could the emptiness of space really be living and moving? What if these levels did more than just pass? What if they changed their minds? Some people in the field of theoretical physics have quietly put forward the idea that Voyager's movement could cause energy to build up in some strange fields. We could be seeing changes in reality that we have never seen before because of the spaceship. Is this the edge of the solar system, or the edge of our understanding? Even now, years later, there's no consensus. The Voyager team has ruled out hardware error. The instruments, though ancient, are still performing within expected ranges, which leaves one terrifying possibility. The universe doesn't behave out here the way it does back home. This is why the last parts of Voyager's mission are so important, not just to remember, for more than just the news, but because they show us something basic that is wrong with the way we think about physics, something that you can't yet learn from books. Voyager 2 was supposed to fade quietly into the dark, but instead it delivered a final riddle, a stream of anomalies, contradictions, and whispers from the edge of everything we know. It didn't just challenge our models of space, it exposed how little we actually understand the universe beyond the heliopause. From magnetic flips to ghost particles and plasma that defies physics, Voyager 2 reminded us, exploration doesn't end when the maps run out, it starts there. If you're ready for more discoveries that break reality itself, subscribe to Beyond Horizons, because out here, the questions only get stranger.